Yeah, hi. Good evening, everyone.
Good evening, sir.
My voice is clear.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thanks for confirmation. Okay, so welcome to all for second week session. So we have this open session basically. If you have open any doubts, then you can raise your hand and you can tell me. So this is the first question from my side. If you have already watched the lecture, so what doubt you have, and if you have any doubts, please let me know. So I'll try to cover all the doubts in today's session.
Sir, so you are not going to summarize the content?
Yeah, that is the last option we have. If you don't have any specific doubt, so we will go to for summary.
Sir,
Okay.
first summarize and then take doubts. It
Yes,
will be
sir.
better.
It will be
Okay,
better.
Yes, sir.
okay, then fine. Okay, so we will summarize the content of B2, and meanwhile, if in between, if you have any doubt, you can raise the hand or you can open your mic and you can ask. Okay, so basically, this is the main week where the okay, someone raised the hand. Yeah, Viral. Viral raised the hand. Okay. Okay, so we will. So this is the main week where the DSA concepts are started now, and the first topic is very important topic. This time complexity. Okay, so we will start from this topic, and this is the topic you will use in the entire weeks for this PDSA course. Okay, so that means time complexity we will generally use for each algorithm. So this should be very clear. Okay, so we will start from the time complexity topic that we will try to focus more. So let me share my screen. Yeah, Viral
Uh,
Chaudhary.
yes, sir. So actually, we are not, what do you say? We are not covering this insertion short and all these things.
No, that we will also cover, but that are actually fixed algorithm. If you have any doubt in that,
Yeah,
that we will also cover.
yeah,
I'll
yeah.
try to finish all the content,
Okay.
but I
Just
think
one
most of
question.
the time will be like this complexity part will take.
Okay, I have just one doubt in one question in selection sort in the activity question. That's it.
Okay, so activity question. Okay, fine. I'll take.
Yeah.
Okay.
23rd is a and deadline. So that's
Deadline. That is
yeah.
deadline. Okay, so
23rd is the deadline for what?
For activity
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 question.
question.
assignments. Okay, so I hope you know. I'm not sure how many of you joined last Friday session or previous session. So this activity assignments contains 3 bonus marks for this course. Okay, additional 3 bonus marks. 2 bonus marks is common like for mock test or like this type of assignments. But the remaining 3 bonus marks are for activity assignments. So because of that, we are releasing these activities assignments as a graded assignments. Okay, with some deadline. And so you can also discuss these activity assignments in your group or in discourse forum. Okay, so there is no, like, we are not stopping this anywhere, so you can also discuss these questions in a or TA session. But after the deadline, TA will conduct one session especially for this activity assignment on Saturday. Okay,
Excuse
so
me, sir.
yeah, sir.
Is it mandatory for all the courses that this practice assignment will give us some bonus mark?
I think not practice assignment. I think that is for bonus. Sorry, mock paper, mock test. Some
Okay.
mock test we release before the quiz one, quiz two, or OPP exam. So that 2 bonus marks is for I think mock test. Okay, and other 3 marks is depends on the course. So what additional activity they want to do, they can assign 3 bonus marks. So for PDSA, we have assigned these 3 bonus marks for activities assignment. Okay. Okay, any other question before starting?
Excuse me, sir.
Yeah, sir.
Sir, for week 2, there is no live coding like extra questions.
No, that is released on Friday.
Okay. Sorry.
Okay, so week one live coding assignments are released on last Friday. So same week 2 live coding questions will release on this Friday, coming Friday.
Okay, sir.
Okay. Okay. So let's start with this. So what topics we are covering in the week 2? So first topic is complexity, because that is required for the whole course. And after that we have searching algorithms, and then we have sorting algorithms. So in this week we are covering three sorting algorithms: selection, insertion sort, and merge sort. One remaining sorting algorithms will cover in third week. Okay, so these are the main content of week 2, and this complexity part is the main important part for this week. Okay, so other remaining algorithms, I hope you know: searching algorithm, binary search algorithm. I hope you have already seen this in your Python course as well. Sorting algorithms are something new, so that we will cover. Okay, so first we will start from complexity. Okay, as you know, in the last week, that Friday live coding session, we discussed some basic questions based on the Python simple logic, and we also found that we have multiple solutions for the same type of same question. Okay, there is a possibility that we can solve the same question with the multiple logic. Okay, so now we have the multiple solution, multiple type of algorithms for the same task. So how we can compare that different solution, and we can come up with the efficient solution. Okay, so because this efficiency is important, how we will select the efficient solution. So some parameters are there to check the efficiency of the algorithms, which algorithm is better and which is not better if we compare more than two algorithms, more than one algorithms. Okay, so now here complexity is the main algorithm function describing the efficiency of an algorithm in terms of amount of input data. Okay, so every logic, every problem has some input, and our logic works on some input and return the output. So how our algorithms depends on the inputs. Depends means so regarding okay, so I come up with the different types of this measure, complexity measures, which we generally use for efficiency of an algorithm. So first is space complexity. So as per the name of this, space complexity. Okay, so space complexity of an algorithm is the amount of memory. Okay, amount of memory needs to run to completion. So when we are running any algorithms, when we running any program, so at that time, the what space that algorithm is taking to store the input, or to store some temporary variables or temporary data which is required to solve that logic or to that problem. Okay, so some memory is required definitely. Okay, to store the input data, as well as some temporary storage to required for some temporary variable during the calculation. So this is space is required, as well as the code. Okay, so that code is also takes the fixed space. Okay, so if we are converting any algorithm into the code, that code itself also takes some fixed memory. So that is also one type of space. So we can consider these two type of space. So first is as a fixed space. So you can see this fixed part. Okay, that is just represent the size of code, and second is variable part. Okay, so that is depends on the input size. Okay, it may be changed based on the input if we change the input size. Suppose we are writing a sorting algorithm, and the sorting algorithms take some input that contain only 10 elements. Okay, so we need a data structure that contains only 10 elements. So that will take only the memory which is required for 10 elements. But we can also pass the different size input like 1000 elements for the same algorithm. So at that time, our data structure size will be changed for the 1000 elements. So this space is basically a dynamic space which is depends on the input. So that
Sir,
is called a, yeah.
sorry to interrupt, sir. Sir, could you explain again that fixed part?
Fixed part is the code actually, code
Means?
size. What implementation you have for the algorithm. So some implementation, you suppose if you have written the algorithms in the Python code,
Okay.
or C code. Okay, so that codes also store somewhere in some file .c or .py file. Okay,
Yes,
so
yes.
that file takes some size.
Correct, sir.
So that is the fixed size for the code.
So you mean like if I have a .py file, so how much size is like 2 KB or 1 KB?
That
That
is,
size.
yes. Yeah, that file, how much size it is taking, which contains the code.
Okay, sir.
Okay.
Okay.
So
Yeah.
that is
Sir,
because of that we are saying that this is
but
fixed part, actually. This
sir,
is the
but
size of the code is
hello,
fixed. Yeah, yeah, Anwar.
sir, but fixed part also changes based on language, right? Like C++ or Python,
No,
whichever language.
we generally not compare compare this space complexity with different languages. Okay, just okay, we are comparing the algorithm or this complexity in the terms of one language. Like we are not comparing the language here. We are comparing the algorithm. So just consider one one setup, or you can consider that suppose if this is the high level code, and it also convert into a machine level code. That machine level code is the same for every language. Okay.
Okay, sir. Okay.
So machine level code, which is actually machine is executing, that is the set of instructions which actually processor understands that machine instructions. So every language actually convert that high level language to into a machine level language. So that machine level language is the same set of instructions. So
Um,
that is the fixed size.
Sir, so you're trying to say like when we are running the, for example, if we have one Python file, so we are running the Python file, we have to give some
Huh.
input. So the total amount of memory that is taking for both run the input plus that file size, that is the total space.
Yes. So what happened when we execute something? So that file actually we are suppose if you are running a Python file, so that code is actually loaded into the RAM memory. Correct?
Yes, yes, sir. Yes, sir.
Okay, so that RAM memory, that code is can load into the RAM memory, and that also convert into a machine code, and that load into the RAM memory, and that instruction one by one passed to the processor and executed. So in the RAM memory, that code also contain takes the space now. So that is fixed actually. Okay, if we are code actually instruct number of set of instructions are same for any algorithm. Suppose if we are writing a sorting any sorting algorithm, so code will remain always same. What will be the change? The size of input which we are passing for the problem. Okay, it may be changed. So we can pass the input list with 10 element. We can also pass 100 element. We can also pass 1000 elements. That the same sorting algorithms will sort the elements.
Sir, like for different sorting algorithm file have different sizes, maybe, right?
Yes, yes. So that is depends on the what logic we have written, how many like instruction we are passing to the algorithms. So that is the that may be different.
Okay, okay, sir.
Okay, so as I mentioned that suppose if we are finding out the what is the sum of 1 to 100, 1 to 100. So what you can do, suppose you can run a loop. So for I equal to 1 to 100, and you can add each number in each steps. Okay, and same
Got it.
time say one single formula you can retain like sum equal to n into n plus 1 divided by 2.
Yeah,
So that
correct.
is single formula. So here instructions are number of instructions are different. So that is logic. According to the logic, this code size also be different. So this, if you see the simple insertion sort, that code size is small. Merge sort, if you see, the code size is big. So that file size may be different. That code set of instruction size may be different. So that is the space complexity. Okay, so if we add both part at the runtime, so what fixed size and what is the variable size it is taking in, how the variable this part is depends on the input. So that is generally this is the fixed part. Okay, but this variable part. So how this that memory which is required at the runtime is depends on the input that represent the space complexity. Okay, and now comes to the time complexity. So this space we are not covering in our course. So time complexity we are covering. Okay, so we will only focus on the time complexity. So comes to the time complexity here. What is the time complexity here? Okay, so this is also a very confusing thing. So time complexity is not represent the clock time. Okay, we are not looking for the clock time, is watch time here. Time complexity of an algorithm is the amount of computer time. This computer time is different. Computer time it needs to run to completion. Computer time represents the number of operations executed by the processor. Okay, when we are running our algorithm. So like suppose if we have one loop set like so like we have for I equal to 1 200. Okay, and we are performing some operation here. So like operation. So or we can pass here say n. Okay, if suppose if n equal to like 10 here. So how many times this operation will execute actually? So this is single operation, but it is depends on the loop. Okay, how many times it will execute? So if we are passing n equal to 10, this operation will execute 10 times. And if we change this value n equal to 100, so this operation will perform 100 times. Okay, so we are looking this total number of operations which are executing at the running time. So this is generally called as a computer time. Okay.
Okay, sir.
Yeah. So now comes to how to calculate this and what are the case we use to calculate the time complexity. So this should be very clear. Computer time, this time complexity is not represent the clock time or watch time. Okay, because we cannot compare the algorithm based on the clock time. Because clock times, clock time, suppose if we account calculating the time complexity like this algorithm is taking 1 second, 2 second like this. So our machine like machine that features may be different. Okay, maybe that processor may be different, processor speed may be different. Okay, so we cannot compare any algorithms on the computer time or watch time. So we have yeah.
Yeah, so when we do lead code or something like, so that MS is same for all.
That means can you repeat what you said
Uh,
last time?
so like we do lead code and you know HackerRank and all these things.
Mhm.
So when we submit our solution, so we get like 10 ms, 50 ms,
So
something
that
like.
is clock time. That is not a time complexity. That is clock time. They are giving you the clock time actually. How much clock time
Okay,
your and that submission is taking. So
okay,
as I
clock.
mentioned that if you run the same algorithm on the different machine, so that clock time may be different.
Okay, so it will be different. It will not be same for like for different
So
machines.
same code. If you run multiple time, you will see that time will change. That time you cannot be fixed.
Yes, the time is changing in lead code for the same solution.
So because of that, we are saying we cannot compare the algorithm based on clock time.
Okay, sir.
Okay, because that is depends on the processor, how many multiple or process are executing on the same machine at that time. So we cannot compare based on the clock this clock time or watch time. So this
Yes.
time complexity is the theoretical concept that actually counts the number of operation or number of instructions which are executing at the running time.
Okay, sir.
Okay, so that instruction will remain same. So this loop is running. Okay, so if n equal to 100, so this operation will run 100 times. If we are running this algorithm on any machine, this instruction will run 100 times. So this is the theoretical count
Okay,
of the
sir.
number of operation. Okay, so this is the time complexity, and also what are the different case when we calculate this time complexity. So these are some case: best case, average case, worst case. So
Sir,
what it is represent?
small doubt, sir. Suppose there is a piece of code, sir, and I'm running
Mhm.
it on a fast computer and slow computer. Will the
Mhm.
time complexity be same for the same piece of code?
Time complexity will remain same, but actual clock time may be different.
All right, sir. Thank you, sir.
Okay. So this time complexity is not a practical fixed time. Okay, so this is theoretical concept first thing. We count the number of operation theoretically. Okay, there is no actually practical way so we can count this. Like there's no like application on tools where we can count the number of steps. Okay, so this is calculated theoretically, and we identify that how the algorithms grows based on the input size. So that we will discuss. Okay, now. So time complexity we are generally calculated in these three type of case: best case, average case, and worst case. So this is also like one example we can understand searching algorithm. Okay, so we have some, like suppose 1,000 element randomly. Okay, some random order. We have 1,000 elements in this list, and we are looking any k element into this list. We are searching. So best case is when if we are searching this element and this element is exists in the initial place. So what is the naive search is actually how the naive search is applies. We start the comparison from the first element and we compare each element one by one till the last element. Okay, and if we are doing this process and our k element exists at first, second, third, or in any initial place, so you need only very less number of steps to compare, and you will get your output. Yeah, this element is.
Sir, can you repeat what is best case? Best case is
best case is when your algorithm is taking minimum time to perform the task. Okay, I'm giving the example. If you have a input link list, okay, that contains maybe suppose n elements. If I'm taking the example like 1,000 elements it contains, and that elements are unordered. Now you are searching some k element into this list that exists or not, or which index it is exists like this. So what process you will follow? So that naive searching applies. So like if you start comparison from the first element, then second element, then third in this way till the last element. So suppose if k exists at the like second place, so you will start the same process. The comparison will happen with the first element. That element is not matched. You will move to the second, and element is matched. So how many comparison happens here? Only two. Okay, only two comparison. You found that the k exists at this this index. Okay, so this type of case is called as a best case when your algorithm is performing minimum number of steps. Okay, to perform the task. This another case is worst case. Worst case is when your algorithm is taking the maximum amount of work. So that means suppose if you are searching k and that k exists at the last place, and you are searching you are comparing each element from the first position till the last, and at the all n comparison, all the 1,000 comparison, after 1,000 comparison you found that yes, k element is exists. So this means the same algorithm now is taking 1,000 comparison. So this is the maximum number of work or steps that algorithm is performing. So this is the worst situation for algorithm. Average case is the average of all possible type of situation. So if element is exist at the first place, it may be exist at the second place. Okay, so like if element exists at the first place, how many comparison will happen? One. If element exists as the second, then two comparisons, then three comparisons. Okay, so all n comparison. If you will calculate the average of this, you will get n by 2. Okay, so that is called as a average case. So average case means all possibility of time. If you calculate the average of all time, that is called as an average case. So our main focus is always on this worst case. We want to reduce this worst case time, because this is the maximum time algorithm is taking. If we reduce this time, so our algorithm will be improved. Best case is already taking with less. Okay, minimum time. So there is no need to improve for this. But yeah, we want to reduce this worst case situation. So we'll always, yeah.
Sir, yes, sir. Sir, for this 1 to n, so if we are finding the average case, then it is not n plus 1 by 2.
That may be a little bit different. So as we said, this is the totally theoretical things. So we ignore some one step, two steps like this.
Okay.
Also, if we are getting this this n by 2 steps, if we want to represent the complexity for this, we will use only n term this term. So that I am coming for that what we actually focus. So the time complexity.
Sir, if we improve the worst case scenario, automatically always does the average case improve as well?
That will also improve.
All right, sir.
So average case is between best and worst case, right?
That is the between thing, but we calculate like this: all possible number of situation how much time our algorithm is taking, then calculate the average for this.
Okay,
Yes,
sir.
Okay.
Sir, but hello, sir. Sir, but average case, best case, and worst case, all sometimes all get to the same value, sir. It may be there like
That is the situation. That is the situation. So we will see for some algorithms. So where our algorithm is not depends actually on any situation. That will always perform our full task.
sir. I think, sir, it depends upon the problem, sir.
That is depends on the problem. So like this searching, we can give this example. So I'll give you the example where there is no best case or worst case situation. Our algorithm takes fixed time for each type of situation.
Yes, sir.
Okay, so that is there is no best case, worst case, we can say that. But generally we represent the same complexity for each case.
We need to improve worst case, everything will be okay.
Okay, so because of that, we only focus most of the time worst case. And this is our main goal, how we can reduce our complexity for worst case. Okay.
Okay, sir.
So I hope this case clear. Let's move to the next part. So okay, how we calculate the complexity or how we calculate total running time like this. So first thing is growth rate of function. So the number of operation for an algorithm is usually expressed as a function of the input. Okay, so each problem have some input. Okay, we can consider what size of input. That is actually a variable part. That input may be changed. Okay, for the algorithms. So that we can consider as a n. So this n term is basically considered as a input. This is not always n. Okay, so this is not a fixed standard term for this input. Generally, we use this. This may be different also. Okay, suppose if any question, if n is given as an input, so you can represent the complexity in the term of n. But generally, most of the time, we use this n as a terminology to represent the complexity. Okay, so now see this example. Now we are focusing on total number of steps takes by our algorithm in the terms of input n. So see this code. If we will run, so this n is the variable part, it may be changed. Now we are calculating the total number of steps, and here also we can this constant part we can ignore. If you're not able to calculate the every part, you can ignore constant things. But I'm calculating the total number of steps in the terms of input size for each step. So if you change of this input size n, suppose if n equal to 10 or it is 100, how many times this first steps will execute when you will run this code?
One time.
Always one time, sir.
Always one time, because this is not coming under any loops or any like nested things like this. So this will always run one time. So this is called as a constant part. Okay, this is called as a constant part. This will always run one time. So I am just counting for this small example to represent the function. Now second loop. Okay, this is a loop for I in range n. So let me just I am considering this n plus 1 because in generally other language C or C things, if we are running a loop, so that I equal to 0 to n minus 1. This is the range when the loop will run. Okay, but in most of the language, there is one steps to terminate the loop actually whenever range is completed.
Right.
Okay, so because of that, I have written this n plus 1. If you are confusing, just you can also ignore this.
Sir, in Python, do they use one extra step to terminate the loop?
So internally it happens, but if you are not able to understand by this instruction, so you can ignore this. As I mentioned that you can cut this if you are not able to. But in generally C, we write the loop like this. So I equal to 0 and I is less than equal to this n. Okay, not equal to n minus 1. Okay. And I plus plus. So what happened? This loop is start from 0, then 1. Every time this is incremented by 1, so like this. And at the last step, when suppose n equal to 10, so this should be 9. But when I become 10, at that time also this condition checked actually.
Yeah.
When I will 10 and this is less than equal to 9, so at that time this condition becomes false and your loop will terminate. So there is
Okay,
one
sir.
condition for the termination.
So, sir, in C, we have to add one for the termination. What about Python, sir? Do we have to add one in Python as well?
Internally, this is happen actually.
So in Python also,
Because
we add a step to terminate.
yes.
All right, sir. Thank you, sir.
Okay, so we can we are running some range. Okay, so we always check that we are incrementing each step one step. So there is steps also comes in this range function. So 0 plus 1 plus 2 every time internally it also checks our new updated value is coming in the range or not. At the last time when our new updated I value is out of the range, that our loops terminate. So internally that is exists. One additional terminate steps is exist. Okay.
Okay, sir.
So this is we are calculating as a fixed count, but that is not much effect on the time complexity. Okay, the sum of one step or two step. So here just consider n plus 1. Similarly, this nested loop, J loop, how many times this will run actually? So for each value of I, like I equal to 0, how many times J loop will run? Same n plus 1 time. N plus 1. I equal to 1, then again J will run n plus 1. I hope it is clear. So this I equal to n minus 1 and J equal to n plus 1. So that means n times we will enter inside the outer loop, n time, not n plus 1 here. So n time we have the n range. For each range we will enter inside this, and this part will exclude. So we have written here n into n plus 1. So this steps will run this number of times. And how many times this operation will execute?
N squared, sir.
Okay, because every J loop we will only enter inside n time. So that means for this line number 4. Okay, so this will run n time. Okay, one terminate steps, but we will enter only n time inside this. So n like this. So we have found this n square, n into n square. And last, this print statement will also execute only one time. Not depends on input.
Sir, for J in range n, it will be n plus 1 squared, no sir? Why is it n into n plus 1?
What you said, n?
N plus 1 squared, no sir? Because this will also terminate in the end. There'll be an extra step for that, no sir?
So that is n plus 1, no?
But it should be n plus 1 into n plus 1, no sir?
No, as I mentioned, n into n plus 1. Because this one is the last terminate step. At that time, we are not entering into the nested function. That is the terminate steps. We will only enter n time inside this.
Okay, sir.
So because of that, we are multiplying n time.
So the n is corresponding to the outer loop and n plus 1 is corresponding to the inner loop.
Yes.
Okay,
This line number 3. Okay.
Yes, sir.
So we have calculated total number of steps for each steps, and considering if we will add all these, okay, so we will get like 1 plus n plus 1 plus n square plus n square plus 1 like this. Okay, so I have added all. So what you will get? You will get something this type of equation. Okay, n square plus n square 2n square, n plus n 2n, n plus 1 plus 1 plus 1 3. Okay. So this is representing the exact number of relation. So how many steps will execute in the terms of input size n. Okay, so this is a function which is representing the actual number of steps. Okay, I hope this is clear.
Yes, sir.
Okay. So now for the complexity, we always focused on the higher order or higher power of n, because this is represent the highest dependency on the input side. This order is representing the higher dependency on the input side. So that for the complexity terms, for the complexity calculation, we ignore all the lower terms, okay, lower magnitude of n, or we can say lower power of n, that we ignore all that part. Also, we ignore the constant part. And we only focused on the highest order term in the relation to n. And that is represent the relation actually. How our algorithms is grow in the terms of input size. Okay, so this is the part where we will only consider to represent the complexity, and we will ignore the remaining lower part and constant part. So this relation is now represented Fn is proportional to n square. So if we will change our input n, like suppose if we have n equal to 10, our algorithm will take steps n square, so 100. If now our algorithm steps is input is 100, so it will take 100 into 100, 10,000. So how our algorithm is growing, like, okay, a total number of steps are growing. So that is depends on this higher order of n terms. Higher order term. Okay.
Hypothetically, if there were, let's say, printf, there were 1,000 printf statements, then it would make a big difference, no, sir?
So that is come. Still, for the complexity calculation or comparison, we always focused on the largest input, not only for specific input.
Okay.
Okay. So suppose if this is n square relation, 2n square relation, this n square. Okay. Another part is n. Suppose n value is like I'm taking very big value, like 10 to the power 6. Next. So for this 10 to the power 6, how our growth will represent this n square, and how, and what is the like for n will be 10 to the power 6, and but it will become very large, 10 to the power 12.
12.
Okay, so this is much bigger than this part. So we always take consider the largest possible input to compare. Okay, so because of that, we ignore the lower terms and constant for this, and we only focus on the largest term or magnitude or power for the input. Okay, so
sir, why we are ignoring constant terms?
Constant, because that is not much effect actually affected. As I said, that this is theoretical concept. Okay, so we not calculate the exact number of steps for this. We just represent the relation with highest magnitude of n, which is actually representing the relation in the terms of input. So how the growth is happening for the algorithm. That is the higher. This is like. Okay, so let me have we have some graph I think for this. I think that is given in the lecture documents, so lecture PPTs. So where we are comparing the algorithm. So if you will make a graph for this, suppose if you make a graph like this, how the growth happen. Okay, like in this case. So if we are taking n this side and we are taking the fn in this side. Okay. So if our function take n square plus n, and we will increase the size, so this higher order term will increase like this. Okay, like this. But in the corresponding this n term will be come up with very lower term. So for the largest input, this will remain very small. So represent complexity in the theoretical things. We only focus on this part. So this is represent the complexity, and we ignore this or lower terms.
What you're saying is the growth of the highest order term is always going to be much more exponentially more than the smaller terms.
Yes, it's smaller term, much more compared to the smaller term.
So that's why we only look at the larger term. Got it.
larger term. Yes.
Sir, hello.
Yes.
Sir, I have a doubt. Sir, why sir s equal to s plus 1 is takes n square?
Okay, this part.
S is
So,
equal to s plus 1. Yes, yes.
on this one. So for suppose I equal to 0, how many times J loop will run? N time?
10 times, yes, yes.
So n time you will enter into this now. So that means this step will execute n time. Correct?
Hmm.
Okay. Then
A,
the upper loop value will become 1.
okay.
Okay. Then this your line number 4 will run again n time. Then I value will become 2 like this n time. In this way you will reach I equal to n minus 1. So total n steps are there.
And
Okay. And each time n is there. So if you add all n plus n plus n times, so how much you will get? N square.
oh, sorry, n square, yes, sir.
Okay.
Okay.
Sir, I,
So now,
sir, I, hello, sir.
yes.
Sir,
sir.
Sir, I have a question regarding the value of answer. When with regard to sir week 2 or with regard to complexity, we will always assume that the n will be a very big number, sir. But in question, if it is written that the n is like 5, 6, or 10, then sir, then the actual the function of fn should be taken, or the number like or the equation like n square should be taken, sir.
So suppose if you have any code written that is written for some specific input. Okay, so like here n is not given. Okay, or if any fixed input is given, n equal to 5. So generally question is not asked for any code which have some fixed input. Okay.
Yes.
So we take the algorithms where the input change actually. Otherwise, suppose if you have any algorithm which always takes the fixed input, that is considered as a constant term. Okay. Suppose if you have written some code and okay, I'm writing some code. Okay, some example is there. I think that is, let me check. See this code. First one. So this code, if you suppose change a and b value.
Yes, sir.
So number of steps will change for this.
Yes. Sir.
No, sir.
No, sir. No, sir.
No, this will always remain 4 steps. If you change any, if you suppose if you are taking input step here, input like this, input or int, you can just type plus to int. If you are giving any input for a and b, this will always run this 4 steps. So that means here total number of steps are not depends on our input. So that type of complexity comes under the constant time, order of 1. We written as a order of 1 means fixed steps. This one is represent not one step. Okay, this represent constant time means fixed step and it is not depends on the input.
Sir, so for anything that has for anything similar to this, the time complexity will always be 1. Is that correct, sir?
If your number of steps are not depends on the input size, if you are changing the input, still your number of steps are always fixed. So that we consider as a constant. Doesn't matter if your total number of steps is still 500. Still you will retain as a order of 1.
Sir, here near the complexity, it's written capital O, then 1, sir. What does capital O mean?
So that is the part which is remaining to discuss now still. Okay, so let's come to that.
Got it, sir.
So I hope this part is clear. So generally, this is the proper thing. So we always we can calculate the complexity like this. But this is time-taking things. You cannot always count all the each single steps in your code and like this. So we generally focus to count the steps. So we generally identify that how our total number of steps are depends on the input size by looking these loops. Okay, this mainly in the iterative codes only looking this loops part. Okay, how our loops are running and how our loops are depends on the input. Are we running nested loop? So how many nested loop we are running? So we just identified that how this relationship we can identify. So you can see this is one n loop. Inside this we are running another n loop. That means total n into n square. So this is just a complexity for of this n square. So we not always count like this. This is just an idea how if any function is given, so how we will consider the complexity. This function is represent total number of steps in the terms of input, but we, for complexity we use only higher order of n. Okay. So now the representation part. So this is the exact relation Fn is proportional to n square. Now how we represent the complexity, that is called as a notation, asymptotic notations to represent the complexity. So we have multiple notations for this. So notations are mathematical notations that are commonly used to describe the time complexity of an algorithm or the upper or lower bound of how the algorithm's running time grows as the input size grows. Okay, so these have some meanings, and these also have some fixed definition for this. How when we will use big O, when we will use omega, and when we will use one theta. Okay, theta. These are generally this big O, omega, and theta. These notations are there. Big O represent upper bound. Okay, omega represent lower bound, and theta represent this tightly bound. Okay, what is this? So now just see this graph. So there are conditions for each type of notations. Let's see this first big O part. Okay, so big O part condition is if your Fn function, okay, Fn function. So this is the Fn actual time, and this some function is given like equal to 2n square plus 2n plus 3 like this. This is the fixed part. So we convert this complete part into the highest order of n terms. Okay, that is we consider as a gn with some constant c. I'll just tell you how we can convert. That means we are looking the upper bound. We can, if we convert this equation into another equation, that where that gn, that we are just considered after converting that equation into another equation gn, and for every input this gn will always be greater than to this time or equal to this time. This is the condition. So that means if Fn is always lesser than or equal to cgn for any constant. So this c is the constant. C, it may be any constant of is equal to 1 or greater than, and another is n naught. This is also greater than equal to 1. This is representing some specific input. After this input, this condition will always be satisfied for any constant. So if we found this cgn part for any function, then we can represent our complexity with Fn equal to a big O gn. Now how we can come up with this? So let's show you the proof things for this.
Sir, with regard to the previous example, could you tell us what is Fn, Gn, and C?
So let's take the same example. Fn equal to 2n square plus 2n plus 3. This is the actual function for algorithm Fn. Now we are converting this expression into a upper bound in the terms of higher order of n. So how we can convert, how we can write like this. So there is a multiple way to convert this. Okay, so I'm just explaining one way. So can I write like this? Fn, this n is the input. Okay, so Fn equal to this 2n square plus 2n plus 3. Can I write like this? This will always be less than equal to 2n square plus 2n plus 3n. Okay, and if for this condition I am taking if n is greater than equal to thing?
1.
Not 1.
But 1 also.
Yes, sir.
1 also make
1 will always give
no, greater than or equal to 1, sir.
N greater than or equal.
okay. Correct. Yeah, so n is greater than equal to 1. If you put this, so if you put 1, then both are same.
Yes, sir.
Yes, sir.
Yes.
Okay, if you put 2, then this will be the bigger. Okay, so we can write like this 2n square plus 5n. This is fine.
Yes, sir.
Yes, sir.
Now we are taking one more condition. Can I write this 5n equal to n square like this? Okay, so 2n square plus 5n. Can I write like 2n square plus n square? And we are taking condition n square is greater than equal to 5n. For this situation, this will always be greater than for this input. So for which value you can prove this?
N greater than equal to 5, sir.
5. Okay. So I have taken this condition. Now I have checked n is greater than equal to 5. Okay. So now put n equal to 5. So this will become 5 into 5. So this is also same 5 into 5. Now
Yes.
at the time both will be same. Now if I take n equal to 6, now this 6 into 6 and this is 6 into 5 inside. 6 into 5 30 and this is 36. Now this part will be greater than.
Yeah.
Correct? Now we can write this as a 3n square.
3n square.
Okay. So now I'm writing like this fn equal to 2n square plus 2n plus 3 and which is like 3n square.
N are equal to 3n square for n is greater than or equal to
But
5.
where we have two conditions, n is greater than equal to 1 and n is greater than equal to 5. We have taken this condition, so we will take the maximum one. This.
Right.
Okay, we satisfy the both. N is greater than equal to 5. So this condition will become a n naught. Okay, now this become a c constant. This become a gn. Okay, in the terms of definition, where what I have written for definition for big O, we need to prove this. Fn is this less than equal to cgn for every input n naught. Okay, every input after this n naught, and this is constant. C is greater than equal to 1. So we need to prove this. If we can prove this, so we can write our complexity Fn equal to big O gn. Okay, so we can write our complexity like this. So that means we are finding out the upper bound. We have finded out the upper bound. This Fn will always be less than equal to this upper bound for any input after this n naught.
Sir, this 3n square is also less than or equal to some constant time n cube. Then why we are not consider that n cube? We are considering n square.
That you can also take. Okay, so as I have said, for upper bound, so this is the upper bound one, but we can also make n cube also as a upper bound. At that, for this also this condition will be fulfilled. You can also take n4. This condition will also be satisfied with this n4, but we only focused for the closest one.
Yeah, closest, like in upper bound we are considering the minimum one.
Which is closest to the function.
Which is closest to the thing. Okay.
Actual function.
Sir, could you once again repeat the calculation? How you got 3, sir?
So 3, I have this 3 C you are talking.
Yes, sir. Yes, sir.
So what I have done, this was the actual function. I have just like reduced this expression in the like in this terms. Okay, so I have just replaced this 3 as a 3n, and I have taken one input. This condition less than equal to will always be satisfied for n is greater than equal to 1. So I have just reduced this expression like this. So when I'm relating this 3n, so for every input n is greater than or equal to 1, this side, okay, so this part, this right side part will always be greater than or equal to this left side part.
Yes, sir.
Okay. Similarly, now we have reduced the 2n square plus 2n plus 3n, 2n plus 3n equal to 5n. Now we want to reduce this term also into a higher order of terms. So I have just make more condition. So this, if we take this, if we replace this 5n by n square term, then our n square is always greater than or equal to 5n.
Sir, why didn't you replace 5n with 5n squared?
Yes, sir. Same doubt.
5n with
5n square. That also we can do, sir.
So,
you can, as
like
you mentioned, there is multiple way to prove this. So as I mentioned here, like 3, you can take any another constant. So suppose like this, what you can do, you can just replace this n with n square. No. So we want to reduce the complete part, no? So 5n term.
Yeah.
So we want to convert that into this higher order of.
Sir, but here you converted the 3 to 3n, not 3 to n. But here you're converting 5n to n squared and not 5 squared.
So because of that, we have just figured out some condition for that, where our function, after reducing our function into the highest order term, for this value n is greater than or equal to 5, this right side will always be greater than or equal to this left side. You can come up with other replacement. If you can prove that your right side part will always be greater than or equal to left side part, you can write.
Sir? From which week is this?
Second.
So C can be anything, right? We just have to prove that f of n is less than or equal to c of j of n.
So let me just come up with your point. So you are saying that 2n square plus 5n, and you want to write like this, 2n square plus 5n. Correct? Sorry, 5n square.
Yeah.
Yes.
Then n is greater than or equal to 1, sir. The condition.
So if you are writing like this, 5n square, then you have to prove this for which n. So this means 5n square is always be greater than or equal to 5n. This is now become a condition. So for which n value, this condition will be satisfied.
Greater than or equal to 1.
1, no? So if you can prove this, you can also write. Now in this case, your n not become 1. Okay. And if you write this 5n square, 7n square. Now it will become 7n square. Now C become 7.
7.
So now you
So,
have to this.
Yeah. So, sir, for this algorithm, provided that we give any constraint, proper constraint, we can give any upper bound to our algorithm. But generally, we choose the closest one, right?
Closer one.
Okay.
So for this function, if I write like complexity fn equal to order of n cube, okay, this is also correct. Okay, this is also correct because in the big O side, this gn part should always be greater than to the fn part. So this is also satisfied this. So according to the definition of big O, this is also true. But for the complexity, we always identified the closest with fn, okay, to represent the complexity. So for we have calculated this 7n square. Now C becomes 7 and n not become 1. So we can write our complexity fn equal to big O gn, and still gn is equal to n square. So n square. So we can use with this big O terms, big O notation. So that
how to identify the closer one? Could you explain that again?
So how we are reducing our this expression into the this single term with the higher order of n, higher magnitude of n. So if you can prove this, if you can reduce this fn, this complete expression into the same higher order of n term, and you can prove this for any n naught or any constant c. So you use this n square.
Sir, could you once again, with doing instead of phi n square with phi n, could you do it like again, sir, and just show us the process how to do it? That would be helpful.
Okay, let's take some another example. Okay, so fn equal to like n square plus 3n plus 2. Okay, I'm getting some other expression. So like this is a function, and we are looking. Generally, this type of question asks just prove that fn equal to big O n square. Just prove this. Okay. So when we can use big O.
Sir?
So if that means if we are looking for the big O definition, that means we have to identify some upper bound for this function. Someone speaks.
Sir, we don't have comprehensive questions. So how it will be asked?
Comprehensive don't we have, but still I am just explaining to understand this. Okay, but you should know how this big O means actually. What is this means of big O? So because of that I'm explaining. But in some subjective, sometimes if you find this type of questions, so you can prove this. Okay.
This is not recorded, no sir.
This is recorded live stream.
Okay, thank you. So we will get the link.
Links will be there in the sheet and channel. Okay. So now this is the actual function, and we want to find out the upper bound to represent our complexity with big O. So this is the requirement for the big O. You have to identify the upper bound at least for this to satisfy this condition. So fn is less than equal to cgn for any n naught value where n is greater than equal to n naught. So this is the central condition, and for any constant c is greater than equal to 1. So this is the definition for big O representation. You have to prove this.
Sir, this definition fn is the same that is given, and cgn.
Yeah, this part you have to identify. So this is the upper bound.
This is the big O.
No, you have. This is the new function. This is the new function gn with some constant, and this is the condition where this condition should be satisfied for every value of input greater than n naught. This condition should be satisfied. So if you see the chart, if you see the graph for this, like this graph, you can see this part. Okay, this is the big O part notation. So just look the middle one. What is this? So initially, for some input, this CGN may be up and down, low and high, but after some specific point, like this is called as a n naught. After this point, your CGN, this will always be higher or equal to this Fn. So you can see this growth, Fn is always lower or it may be equal also. So this CGN you have to identify, that is called as a upper bound for this algorithm. If you can identify this CGN, you can write your complexity with big O notation.
Sir, sir, please identify omega as well as non-omega graph also.
So this is the omega notation. If you can identify the lower bound is the minimum time which algorithm can take. So that means your function can take equal to the CGN or will always be greater than this. So that means this is the time which is the minimum time for your algorithm. So that is the lower bound. Okay.
So could you please repeat the tightly bound, the theta one again?
So for tightly bound, you have to identify both upper bound and lower bound. If you can identify both, then you can also write your complexity with theta. That is a type. That means your Fn will always be lies between this upper and lower bound. So condition for this is simple.
Condition checked by 3 functions.
Sir, here big O will have a function Fn, sir. And then you said that the time complexity, we should only see the biggest exponent or whatever, n square. If it's n squared and n, we should only see n squared. After that, where is this O? I didn't understand why we're trying to find upper bound, lower bound, and how are we using these O, omega, and theta? Like, I didn't understand the connection, sir.
These are the notations which reflect something. So that what it is reflecting, this is the like upper bound is equal to the worst case. Okay, so we are identifying the complexity like as a worst case relation. So this is the maximum time your algorithm can take. So this CG, this lower one, middle one. Okay, so that means for the algorithm you are figuring out that the maximum possible time your algorithm can take, and that you can, if you can prove this, you can represent your complexity with big O notation. So that will also reflect this is the complexity in maximum time, like worst case.
So, sir,
Okay.
when we
This is represent as a best case type of things.
so sir, for any algorithm, if we calculate the big O and the lower bound, suppose, so is that equal to finding only the tightly bound thing?
Huh. So for if you are able to figure out upper bound, if you can prove the lower bound also, and you can prove that your Fn will always be lies between in this range. So you can use this theta notation. For the same, you can, because this tightly bound also contain this big O condition, it's also satisfied. So you can also represent the same complexity with big O. Okay, and this tightly bound also contain the also satisfied the this omega definition. So you can also write the complexity with omega notation.
You're previously explaining the steps to with the polynomial, how to derive the constants. Could you please continue that, sir?
So this is not like as a this big O will always be different with the omega or theta. Here to use this, we need some proof actually. So which notation we are using, you should have that reflects something. That means if you are using big O notation, so that means you have some upper bound for that. Okay. So that means that your algorithm will not cross that upper bound. So that means if you have that much information, so you can use lower notation. If you have only this type of notation, that means you have lower bound for any algorithm, so that you can use omega. If you have both bounds, upper and lower bounds, then you can also use theta.
Sir,
So this is just a representation.
Sir, this n naught representation is what it tells, like intersection between in the first scenario is not intersection.
No, n naught is the any specific input. After that input, this condition will always be satisfied. So n naught is just a one point of input. Once like suppose it is starting 1, 2, 3, and this is the 0.5. So before 5, you can see this Fn may be this lower, and then after that it is higher to the CGN. But after this n naught point, this CGN will always be higher or equal to Fn. It cannot come to lower side. So this is the definition for it.
Sir, could you again derive how you're getting from Fn to Gn, how to get CGN? Could you please derive that, sir?
Yes, sir.
Yeah.
So we are interested in best case scenario. Huh?
Worst case.
Why worst case?
No, so worst case, best case is already smallest time. So how much why you want to improve that best case? We want to improve our worst case situation, so that will improve our algorithm actually. So like suppose a searching algorithm. So best case is one constant time. So how much more you can improve? Worst case, which is we are taking, and like if you can improve that, that will be your achievement. Okay, same for sorting algorithms you will see like this. So okay, so for this function, so for this function,
So we are finding a big O only, no? In this case.
Because generally for whole course we will use only big O notation, but you should know what is the meaning of this big O actually. So for the same expression, I can prove that with the all notation. So like this Fn equal to n square. So I can write n square plus 3n plus 2. This will always be less than equal to if I write n square plus 3n plus this. If I replace this completely 2 by n. Okay.
So can you
Not
do 2
2n this time. We can also do 2n. Okay. This time I'm also writing only n. So as I mentioned that this can be proved in a different way. So can I write this n is equal to greater than equal to 2? This condition, this is left part and this is right part. Right part will always be greater than equal to for this n.
Yes, sir.
Correct?
Yes. Yes.
Okay. So now this become n square plus 4n. Now if I write like this is greater than equal to, now I am changing 4n completely, this 4n with n square. So that means n square plus n square, and for this is n square is greater than equal to 4n. Okay, so that means n is greater than equal to 4. This input. So for this input, this will always be greater than equal to this left part. Okay, so this will become a 2n square. Now our complete expression is reduced in this required CGN part. Okay, so CGN. So now which for which common input with this both condition will be satisfied?
4 greater than 4.
We select upper one. So we can directly write now fn this function. Okay, this is the initial function, and this is always be less than equal to CGN. Okay, so CGN is 2n square. For which n naught? N is greater than equal to 4.
4.
So this is now become a n naught.
Got it, sir.
Okay, and this become a C. So now we have all the satisfied things by this proof. So we can this become is Gn. So we can write our complexity like this: Fn equal to big O n square. So this become n square. Now for the same function, how we can prove the omega notation? So same function Fn equal to n square. This is easy proof. 3n plus 2. Now we are looking only the lower bound here. Okay, and lower bound that should satisfy the condition that Fn this should be always greater than equal to Cgn. Okay, Cgn for any input n is greater than equal to n naught and any constant c is greater than equal to 1. Like this. If you can prove this definition, so that means your Cgn will always be lower. Okay. So now can we write, and this Gn is generally with the highest order of n which we have. So if how you can reduce this expression? So let I just remove this part from this. So can I write this n square plus 3n plus 2? This will always be greater than equal to only n square. I just remove this part. For every input n is greater than equal to 1. Can we write this?
Yes, sir.
Okay. So now this n naught n is greater than equal to 1. 1 become a n naught. Here we can write like 1 into n square. So this 1 c become a 1. So again our definition is satisfied for omega. So this means this become a Gn. So same we can write like this: Fn equal to omega Gn or Gn n square. This is also true for this function. Okay. And now you got both upper bound and lower bound. We have proved both. So you can also use the definition of tightly bound is if you can prove Fn. So that Fn is always be greater than equal to C1 Gn. Okay, and this is less than equal to C2 Gn.
Sir?
If you can prove this.
Sir, in the previous one, like you're finding the lower bound. So in that case, so n square plus 3n plus 2, which is greater than or equal to n square, that is fine, sir. Like it is all like n square plus 3n plus 2. It is always greater than or equal to 3n plus 2 also, right? No, sir. Why we are choosing n square in specific?
Again, same closest lower bound. We always reduce our expression into the highest order of n.
But sir, upper bound is also n square and lower bound is also n square
Huh.
for this function.
Yes.
But C is different, no?
These are C and input. These are different things.
Sir, so our final goal would be to final goal will be the upper bound or lower bound, the G function. It should always be with the n squared, or let's say if the highest was n to the power of 5, then it should be with n to the power of 5. We should write it in C into some constant into n to the power of 5, like that, no, sir? Is that correct?
Like this.
Okay, sir.
Okay, so this is the definition you have to prove with some constant. So like this tightly bound definition is this, okay, for any C1 and C2 which is greater than or equal to 1, or any n naught. Okay, so here you can, again, we have already done this part. This is as a lower bound, okay, and this part as a upper bound. We have already figured out the C2 Gn and C1 Gn. Okay, so we can, if we can prove this expression, so that we can also write Fn equal to theta Gn on this order of n square, like this. Okay, this is just a proof things. If you are not able to figure out that lower bound, that you have only upper bound, then only use Fibo notation.
Sir,
if you are only
sorry, sir, to interrupt. Sir, here it's theta Gn squared or Gn?
Gn, but I have cut this actually. Instead of Gn, I have replaced this Gn value n square.
Okay, so sir, when we I understood how we come from Fn to On, sir. So how to interpret, how to reverse engineer it, sir? Suppose if we have something like, if you have this On squared, how to interpret it, sir? That.
So that means this is the upper bound, actually, upper complexity for our algorithms. That means the worst case maximum time for our algorithm.
So sir,
and that complexity is representing n square. That relation is representing n square.
So what we are saying is that the worst possible case is some constant into that function that is inside that On. So here, let's say it's n squared. So the worst.
But for complexity, we only use the highest magnitude of n. So that complexity will represent in the terms of Gn. But this big O represent that this is the maximum complexity.
Got it, sir. So when we see On squared, that means we are interpreting it as the worst possible.
Worst case you can. Worst case
is
possible.
C into n squared, right, sir? Not just n squared. C into n squared, right, sir?
So if you convert that into the same previous step, so you have to you can write like this: Fn equal to reverse engineering is this complexity is given, so that means your Fn is less than equal to Cgn. This is the actual condition when if you are writing the complexity like this.
And here Gn is n squared. Got it, sir. Got it.
So, as I mentioned that for the n square, we can also write like complexity Fn equal to big O n cube. This is also correct for this function. Okay, this is according to the definition. This is also correct, but this is the closest one. So generally, for complexity, to represent the complexity for any algorithm, we write the closest one complexity. So I think some questions are there in your assignments where this type of things are mentioned, like you have a best case complexity. Best case complexity is like A1, okay, and average is A2, and worst is A3. So how we can represent? So best is the smallest time, average is the middle time, worst is the maximum time. So this is just represent the time actually. So can we write like this: A1 equal to big O A2? Can we use this? So some I think some questions are there in the assignments. So we can use this because according to the definition, this part, this is if we consider this as a Fn, okay, and this part considered as a Gn. So that means this this condition should be satisfied. Fn is equal to less than equal to Gn. So means best case will always be smaller than or equal to this average case. So this is 2. So this can be written. But we cannot write like this: A2 equal to big O A1. Then this definition may be false, because best case will always be the smallest time. Okay, average case may be the greater time. So we cannot write this here, because now this definition will not be satisfied.
Sir, A2
Because
equal
this
to
part may
omega
be,
of an. That is right, sir.
A2 equal to
Omega of an.
that is correct. A2 equal to omega A1.
A1.
So now this is representing this can be smaller. This part can be smaller to or equal to this A2.
Right, right.
So that is true. Okay, so for comparison, if you know that this is the smallest, this is the maximum, and this is the middle anytime, you know that this is the smallest amount. So how you can write this omega and big O and theta things? Yeah. Okay, so these are three notation. We will use only big O notations in this course. So you should know how why we are using big O and how this is actually what is the meaning behind that.
On the top right corner, sir, you wrote f of n is always less than equal to cgn, no sir? So here c is always greater than 1, no sir?
Greater than equal to 1.
Greater than equal to 1. So we can convert this statement into fn has to always be strictly less than or equal to gn. We can write that as well, no sir? So that
that is true, but some constant in the definition, some constant or input is required. But with big O, we only write the gn part.
Right, sir. So big O. So okay, sir. So if we have fn is less than equal to cgn and c is greater than 1, that implies that f of n is always less than or equal to g of n, no sir?
What you said, fn is less than equal to cgn and c is always greater than 1, you are saying, eh?
Yes, sir. So that implies that f of n is always less than or equal to g of n.
So gn is the only highest order of fn. Fn is complete function, like 2n square plus 2n plus 3 like this. But gn is only the term of the function with only this order.
Okay, sir.
And like 5n square like this.
And
So
got it, sir. Got it, sir. Thank
you. Okay. So we have converted our reduce our function into one term. That is the highest order of n. So after that, we are using this as c, and for some input n is greater than equal to n naught. So that is satisfied our definition of notations. Okay. Yeah, Akanksha.
Sir, here the value of c is any positive integer, or we can take real
positive integer. Positive integer.
Only positive.
Greater than equal to 1.
Yes.
Okay. So now these are the notations. Okay, so we will consider only big O notation most of the time represent the complexity of each algorithm. Now comes to the next part of this. Now you will see this big O everywhere. Okay, so we are only using this notation. So now the growth rate. Okay, here are some common function and their growth rate listed from slowest growing to fastest growing. So these are some very common complexity for algorithms which you will see most of the time for complexity. Okay, so what it is represent big O1. This is the constant time. Okay, means a fixed number of steps. That is the constant time. Log n. Okay, so I'll give you the example for this log n, how you will get log n type of complexity, and sometimes square root of n. Okay, so this is the increasing thing like this. So this is the smallest time. This is after then. This is greater than constant time. This is linear time. Okay, this is n log n linear arithmetic time. This is quadratic time. This is n cubic time. This is exponential time, and this is factorial time. So this is the highest. Okay, maybe you will find out that for some. So as I mentioned, that don't compare these complexity for some smaller input. Okay, So at that time, maybe you will get some different things. So like this is the biggest one, n factorial. Okay, this is the exponential time. Suppose n equal to like 3. So for 3, this will become 2 to the power 3 will become 8. But this n factorial 3 into 2 into 1, this will become 6. You can see this is smaller. Then why this is coming after this 2n. But for the bigger value, bigger n value, you will see this is the highest growth, maximum growth rate. Okay, so this is the order in increasing way. So most of the time, this complexity will come in this type. So now let's see some example to identify the complexity. So this is we have discussed. This is the one code where some input we are giving. This is the fixed input, or you can also read this input from the user. Then it will become a dynamic input. So in this type of case, your steps are totally not changing. Okay, so that means this is the constant number of steps. So you can write the complexity below 1 directly. Now, second example, you can see here n input we are using, n term, this n will be changed. So we are considering this n as input. So if we change our n input, this part will actually depends on the input size. If you pass n equal to 10, this part will perform 10 steps. If you change this n equal to 100, this part 2 and 3, these will perform 100 times. Okay, so this is the dynamic part, depends on the input. So
what happens after n minus 1 iteration?
n minus 1
iteration, like, it will again go into a for, no?
No, what you are saying for I in range n means what
yeah,
you
you said this line will be n plus 1 times. No? What happens after n minus 1 iteration?
Okay, so as I said that we have considered to count that total number of steps. Now we will consider the approx steps. So do not just much focus on this n plus 1 steps, terminate steps. Approx. So suppose if n equal to 1 lakh, okay, 10 lakh like this, okay, and you will add 1 this. So how much it will impact into this last number? So we ignore this smaller things like terminate steps. If you are not able to understand this, what is this additional step? So just consider only n part, okay, for this type of loop. So this is the loop which will run only n times. This part, this I am talking about the complete part. This will run total n time. So that part is depends on the input and directly depends like linearly. So if input is n, your total number of steps will be here. Because as I mentioned that if you count the total number of fixed steps, so this will become this is 1 plus this will become like 2n. I'm just writing, like, ignoring that one, okay, 2n. So still we are only focusing on this n part. So we will represent our complexity order of n. We will remove this constant, and only focus on this n. So for this part, our complexity is order of n, and this is just a constant. So overall complexity will become a order of n for this complete code. So that means if we change the input, this is our total number of steps are linearly dependent for this. Now nested loop. So nested loop you can see. So we have already discussed this. So how our steps are depends on this. So this is totally what is the maximum terms? N square. If you will calculate the function for this, so maximum term is n square. So n into n square. So we will only use that term. No need to write complete 2n square plus 3n plus like this. Just only focus on this maximum order of magnitude of n, this power of n, so which is depends on the input. So this nested loop means this internal part is n square. Okay, so this is the maximum type, maximum term. Just only focus on this n square, and the complexity of overall this will become order of n square. If this is 3 times, so this part is will execute maximum number of times. How many times? N cube. Okay. So overall complexity order of N cube. Now there is one combination way. So that is important for this complexity terminology. Suppose if your code is written in this way, multiple part and that is performing sequentially. So what will be the complexity? So you can also, if you have this type of code where some part of the code is completed first, after that second part is executing, then after that third part is executing, like this. So you can break your code in multiple way if that is performing sequentially. That means this part, okay, so this or we can say this part completely is not coming under for the previous part. So that means once this part will complete, then you will reach at this fourth number of steps. So that is sequentially part. When the first, suppose if I am just considering this P1, this as a P2, and this as a P3. So once P1 will complete, then only P2 will start. Once P2 will complete that, then only P3 will start. So you can also calculate the complexity of each part separately. So what is the complexity for this part?
N.
Order of N? What is the complexity of this part?
N square.
N square.
N square. And what is the complexity of this part?
N cube.
N cube.
So now 3 part which is performing sequentially, so that we can also write the complexity function like this: n cube plus n square plus
n.
We'll only focus on this highest
N cube, yeah.
So overall complexity is now order of n cube. Okay, so we select the maximum one if we have this type of sequential code. Okay.
So we could similarly do it in the polynomial method, and then at the end, the biggest term will always be n cube. So we can just write n cube. Can we, instead of breaking it and all? Is that also fine, sir? Like if we take this whole as one.
Easy calculation. Whole as one, still you will get the maximum number of steps this will take.
N cube. So we can just directly write O(n) cube. Is that fine?
So you can identify that in your code which part is actually taking the maximum number of.
Got it.
Okay, so you can directly use that. This is for easy calculations. You can break your code into multiple sequential steps, and you can calculate the complexity for each part and select the maximum one. So that is the complexity. And next thing is like, so this comes in recursion. So this is the iterative course. Iterative course just focus on the loops. Okay, how loops are dependent on the input, how the internal function. Okay, so let me give one example for the log n time. So how the log n times comes. Suppose you are running a one while loop. Okay, you have started I equal to 1, and now you are running while when I is less than equal to n. Okay, then you are running the internal part, and internal steps, how you are increasing I equal to like 2 into I. So like this type of code is there. Now you started 1, suppose n equal to like 1024. This is the n value. Okay, and your I is initially start with 1. So first step I is equal to 1. I equal to 1. Then this loop is 1 is less than 1024. Condition is true. You will enter inside the while loop. Now this I will change, and every time it is multiplied by 2. So 2 into 1, it becomes 2. Okay, next iteration. Now 2 is less than 1024. Again you will enter. Now this become a 4. Okay. Now again next iteration it will become a 8. Now next 16. Now 32. Now 64. Now 128. Now 256. Now 512. Now 1024. And next step 2048. At this point, this loop will terminate. So here n was 1024. But how many steps your code is performing? That is actually, if you count it, this is equivalent to log n. Log base
2. Yes.
So this 2048 will run or not?
This part is the terminate condition. The 1024 where the value is matched, but where you will enter inside this. Again, your I will increase to 2028. At that time, this condition will become false, and that's
Sir, so the precise statement would be log base 2n plus 1, but we'll ignore the 1.
We will ignore the 1.
Okay, sir.
Okay, so this is the only part. So in this way, like you can see, your steps are increasing not linearly one by one. Here your steps are increasing by twice every time. Okay. Similarly, suppose if I start like this value n, and now this is condition is reversed, like if I is greater than equal to 1, and every time what we are doing, I equal to I divided by 2, or float division like this.
Same,
Okay,
sir.
this is just a reverse things. So that means we are starting 1024. Now this will reduce to 512. So same way, this reverse order, your steps will done. So how many steps you are performing? Every time you are dividing by 2, and you will get log n steps to stop this process. So you are getting this log n things. And same you will see in the binary search. So in binary search, if you know the logic, we just look the middle element and we discard half of the part of searching at every steps. So initially we have n element to search. Next step we have only n by 2 element to search. Next time we have only n by 4 element to search. So in this way, this is reducing to till 1. So that total steps are only log n. Every time you are reducing half.
Sir, log n with base 2, no, sir?
Base 2. So in this course, if log n is written, always consider as a base 2. Okay? If without base is written, do not consider base 10 or something. Okay, so this is the log n time of code. How we are getting log n time. So yeah, so this is the way to calculate the complexity for simple iterative code or some which are directly depends on the loops or something. You can directly identify the complexity. But we will also see the code which have some recurrence function. Like this recursive function. And you have already seen multiple algorithms now, merge sort with recursive function, quick sort with recursive function. So how we will calculate the complexity for recursive function. So for recursive function, we have different way to calculate the time. Because in the recursive function, we call the different same call to the same function from the inner body. So we have to identify the complexity, or we have to also identify the total number of calls. So we have to figure out. So there is a different way to calculate the complexity for recurrence function. So just understand the complexity for this factorial function, and we will see the remaining part, how we calculate the complexity and what are the method. So for this function, you can see this is the recursive function. That means internally we are calling the same function again. So if you want to calculate the complexity of overall, that will also come up after adding the complexity of the recursive call. So that means if we are considering Tn is the total time for the function, that will be identified by the recursive call. That means time of the recursive call. And apart from this recursive call, what is the complexity for the remaining part? This part. So that is written here. Okay, so Tn equal to, that means time of the total this function, initial function total time is the for n input, but internally we are calling again the same function. That means this is the same again, Tn minus 1. Here the input is changed, okay, n minus 1. But this is the recursive part. Okay, but apart from recursive part, what is the complexity for the remaining part, which is not recursive? So that is constant. Yeah. So that is written as a order of n, or sometimes we also said that fn, this part. Okay, Tn equal to, this is the recursive part, and this is the complexity for the remaining part. Or sometimes you will also see on without this big O, only one. That is also fine. So this is called as a recurrence relation. So to calculate the complexity of recursive function or recursive code, so first thing, identify the recurrence relation for that. Okay. So after getting the recurrence relation, then you can calculate the complexity with the help of recurrence relation. So how they are calculating the?
Sir, can you explain the same example, assuming that inside the recursive function there's a for loop?
Inside the recursive function,
There's a for loop. There's a for loop inside it, sir. Instead of if, there's a for loop, let's say, sir.
So that what will be the complexity for remaining part? Order of n.
Will it be n squared? N squared, sir? I'm assuming n squared.
So that way we will come up after the solving the equation. Okay. But so that means I'll also give the example how that recursive function calls multiple times. So how we will write this recurrence relation. So that means when we are writing this Tn, this is the total time equal to, we write how many times we call the functions and what is the input. What is the time for that? So here we are only calling one time. Okay. So we only written T. If we call the same like 2 times, so we will write 2T. Okay. And what input size we are passing to the new call, that we are written here, Tn-1. So that means this is the, again we have to calculate internally. But apart from this recursive code part, what is the complexity for the remaining part? Code. So that is only fixed steps, and that is constant. So that is written order of 1. Now how we will solve this equation? Actually, this Tn equal to Tn plus Tn-1, this one. So this is the easier example, but we will come up with the more different type of recurrence relation. So we have written Tn equal to Tn-1 recursive part plus non-recursive part time complexity, order of 1, or we can consider as a 1 to solve. Okay. So this is the Tn. We are writing this expression as a full this line. Okay. So we can also write, if we change this input Tn, instead of n, we are writing now Tn-1. So how you will write the new expression for this?
Tn-2
2
plus O1
plus O1
plus 1
plus
or 1
existing O1.
1. Now instead of this part, write this. Okay. So in the initial expression, so Tn-2 plus 1, and this was the previous plus 1. Okay. So this is now same things. This is again Tn-2. So now what we will write? Plus 1. So instead of this, replace this Tn-3 plus 1. Now previous part this one. Okay, so plus 1 plus 1. So you can see we are expanding like this. Okay. Now n-3 we have 3 1. Okay. Now Tn-4 we have total plus 4 times 1, or we can simply write 4 if we will add all this. So how many times you will reduce 1 1 1? N times. Okay. At the last point, if we see Tn minus like n-1, so this will become a n-1. Correct. This was 4. This was n-1. This is n-1.
So T of 1 is 1. So that
So
makes up solid n.
Yeah, T of 1 is the base case when your recursion stops. Okay. So that is 1 time. So that become T1. So that is a single step. So you can see n-1 plus 1. So total become n. So overall, if we add all these steps, we are getting total n steps. Order of n complexities for this. Okay, so this is the simple recursion for factorial. We got this recursive function, but we have different type of recursive function for what is that? Akansha. Yes.
Sir, orders 1 is a constant value, right? So you have taken 1 here.
So that is constant because to calculate the total number of steps, we are taking 1 at each step. So this recurrence relation we will always also find with like this Tn equal to 2 Tn by 2 plus 1, okay, or only n like this. So this is the multiple way to represent the recurrence relation. You can also write only steps, or you can also write with complexity order of n like this. So both are fine.
Yes.
Okay. So this is the example for this basic simple factorial function.
Sir, in that recursive function, I have a simple doubt, sir. Like, scroll up, sir, like bit. Like, if it is instead of n times factorial of n minus 1, if the return function is factorial of n minus 1 plus factorial of n minus 2, then how this function is actually processing, sir?
So that means you have 2 call.
Yeah.
Okay. So before that, okay, so you are calling 2 types. So how the recurrence function related? So like Tn, now 2 calls are there. 2, or you can write like if you have different input, Tn minus 1 plus Tn minus 2
minus 2. Yeah.
plus 1.
Plus 1.
Like this. So here 2 calls are there. So that you can understand that here only one, this is the constant difference. Okay, so n minus 1 or n minus 2. So if you draw the call structure for this, so you Tn is the first call, but from this there are 2 calls, Tn minus 1 and this set Tn minus 2. Okay, and now 2 calls, again this will divide into 2 calls like this, and each have one constant time, one fixed constant time. So plus 1 from this set, plus 1 from this set. So in this way, Tn minus 2, Tn minus 3, and this is Tn minus 3, Tn minus 4. So this will grow like this.
Okay.
Here the total steps are 1. Now in this level steps are 1 plus 1 2. Here there are 4 calls, so total steps are 4. I am just adding this step, okay, apart from the call. 4. Now next level 8 call will be there, so that 8 steps. So that means 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and total n time, because you can see this side n minus 1, this n minus 2, this part is actually moving n time. Total n level will be there. Okay, so at the last step we can consider 2 to the power n steps.
Okay.
So you are getting this type of expression 2 to the power n plus 2 to the power n minus 1 like this. Okay. So what is the highest order of complexity? 2 to the power n.
2 to the power n.
2 to the power n complexity will be there.
Okay. Sir, like if we have a return statement with the 2 recursive function with addition as operator, so in Python first it will complete the first recursive part, then it will go to the second recursive part, or it will do parallelly.
Generally, that is different things. Parallel processing, parallel computing. It is a different thing, but generally this part will complete first.
Okay, then the second will go.
Once you will get the return from this, then this will move to the back, then this will expand like that.
Okay, okay, sir.
Okay, so this is just like a 2 to the power n example when we are calling 2 times, and let's come up to the different example which you have seen in the merge sort. Okay, so merge sort, if you have seen the code, there are 2 functions actually. One is merge. I hope you have seen the code.
Yes.
Okay, so there is one recursive part. This part is the recursive part. Okay, where we are calling 2 times this function, merge sort itself. Okay, and this recursive function is calling on the half of the input, both actually half of the input. But apart from, so this is the recursive part, you can see this is the recursive part. But apart from this 2 recursive call, we are also calling a merge function. Okay, and this is a constant part, but in this part, this is a one call, and that call is actually, if you calculate the complexity of merge function, that is order of n actually operation. So I hope this you have seen the implementation. Let's show you. Find research last night.
So it makes sense actually. In the end, we would have only one elements after all the splits. So if there are n elements in the list, then we would have one elements for the element-wise comparison during the merge, right?
So in this C, you can see this merge algorithm. So this is just a iterative code every time you will see. So we are running a while loop for m and n, and this actually we divide each time half of the input each time. So this m or n value will be the equal actually most of the time, or maybe one or less, one less. So that means both are the same. So we can consider this as a order of n complexity for n input. This merge function. So now for the complexity calculation, how we can write a recurrence relation for that?
Sir, what is the relation between A and B and N? Max of A and B is N or min of A and B is N? Or the length of A, length of B?
No, so what we are passing to the merge function, we are passing two lists, okay. Initially we are getting the A list. This A is the unsorted list. After we are performing the process and we are dividing that list into a half part each. Okay, n by 2, n by 2. And both lists we are passing ln as ln r. So that is passing to the A and B. So now this is the n by 2 size, this is also n by 2 size. But when we merge this, we run both like these number of maximum steps, n by 2 plus n by 2, that become n steps. Okay, so this function takes, if we are getting two list of n by 2 size, this function takes the total number of n steps, or we can consider order of n complexity for this merge function. So for this recursive function, we can consider that there are two calls. So total complexity, what we can written Tn. How many calls we have? We have two calls. Okay, and both calls have the n by 2 input. Now, initially main call has the n input, but internally we are calling two times. So that means 2t, or if you can write t n by 2 one call plus t n by 2 another call. But apart from this two call, what is the complexity for the remaining part? So this is the one function call of order of n function. So that will be the complexity for the overall remaining part. So we can set write like n or order of n. Okay. So we can write recurrence relation Tn equal to 2t n by 2 plus order of n. So this become a recurrence relation for merge sort.
Sir,
so you can just yeah.
This will not this will never ending loop.
Sorry.
This is recursive means never ending, na?
No. This will end actually. This is the base case, no? Recursive function always contains the base case. That is the terminate point. We are not going to the infinite number of recursive calls. So always recursive function written in this way that contain a base case for terminate, stop the recursive call process, or it contains the recursive part. When our base condition is not satisfied, then we will only call the recursive. So every times we just move in this way. So like we will always reach to the base case. So here what we are taking, you can see every time we are reducing the size of our input. Okay, so initially we have a list completely with n input, but after that we have reduced the size n by 2. Okay, again in the next call it will become n by 4. So in this way it will reach to the 1. So this become a base case. When our n is less than equal to 1, we will directly return a without calling this part. So this is the return stop point.
Sir, how do you go from recursive relation to complexity, sir? I did not understand.
So that is so first step, just identify the recurrence relation. This is clear or not?
Yes, sir.
Okay,
Yes.
so if you have any recursive code, how you can write the recurrence relation? So just identify total number of calls. If each call has same input, so you can just add that call total number of calls like this 2t n by 2. Apart from the recursive call part, what is the complexity for the remaining code. So that is just this. Okay. So now, after getting the recurrence relation, there are multiple ways to calculate the complexity. One way will be discussed in week 8, that is a recursion tree. That is the recursion tree method. Okay. Another is mathematical way is just expand this expression. Okay, just by putting each part again and again like this, and come up with the mathematical. Just solve the expression mathematically and just come up with the answer like we have done for the factorial code. So we got this relation Tn equal to 2Tn by 2 plus that 2Tn by 2 plus that n. Okay, we got this. So just put like this 2Tn by 2. Suppose if Tn by 2, if you pass this, then what will be the expression? So like you can write 2Tn by 4 plus n by 2. You can write like this. So you can replace this expression and 2 multiply and like this 2 Tn by 4 and plus n by 2 plus n like this. Okay, in this way. So you can one step you can just expand this expression and get the idea of how this expression is coming and solve mathematically. This is the one way. Recurrence relation, I am giving the example how you can by the recursion tree how you can solve this. So just identify the structure of tree structure. So Tn, this is the first call. After that you are getting Tn by 2, Tn by 2, correct? This. Again, next step Tn by 4, Tn by 4. Same Tn by 4, Tn by 4. Like this, okay. So in this way, if you will count the total number of operation apart from this calls, okay. So when we have this Tn, so total number of steps was n at this level, correct? So now when we have called this Tn by 2, you have plus n by 2 in the recursive like 2Tn by 4 plus like n by 2 this. So n by 2 from this side, n by 2 from this side. So this steps is actually coming when we are merging the things. Okay, so like again Tn by 8, like this Tn by 8 in this way, 8 steps. But when this dividation happened, when we reached at the T1, then reverse process happened, actually merge process. So we will come up with the merging process. So suppose Tn by 4, Tn by 4, we merge this. So we got this like sorted list of n by 4 size, sorted list of n by 4. We merge into n by 2 size. So that is the merge steps actually come. So that merge steps is taking.
Sir, I want to ask this where we other than the recursion is ending in the plus side, is also being like divided if left one is also divided.
I'm not getting your point. What you said?
Like left side is like the recursion part and other is non-recursive part, na?
Okay.
So here the scenario where told that the second when we multiply it, then we add it to plus n. Is it the part we are able to? Are you able to understand that?
Multiply where we are doing this. This part you are saying multiply.
Yes, sir.
So this is the expression we are calculating. So how this our additional steps we are getting and how you will get this number of steps. Next time you will put this Tn by 2 what you are getting. So that again you will get expression like this. So n by 4 that will become a like 2Tn by 8 and plus n by 4 like this. So just put this expression at the place of this. So this 2 is by default coming at the each steps. Okay, but this is like a constant part. Okay, we will come up with some additional things. So we can also consider So this is the mathematical things, not always easy to calculate. So because of that, multiple different ways is there. As I mentioned that if you're not coming up with by this way to solve this expression, this is the another way to calculate. So I'll explain you how you will easily understand that how we will get the n log n complexity for merge sort by this way. So recursive way. So this is complex expression we are getting. We can, if you can come up with the solution by mathematical way, that is fine. Otherwise, different way we can use for some case. So this recursive tree structure, if you see, merging process actually taking by merge operation is taking order of n time. So when we are merging like from this point, okay, so 2t n by 2 plus n. So you can see n step are there additionally for this level. Now when we are coming to this point, so we will get merge from the lower side. Okay, so t n by 2 we will merge this to n by 2 steps, n by 4 plus equal to n by 2 steps. So at this point n by 2 by merge and this point n by 2 by merge. So if you add both n by 2 plus n by 2 at this level, again n. Okay, from this point, this next level n by 8 plus n by 8, you will get n by 4 steps for merge. Here also n by 4, here also n by 4, here also n by 4. So if you add this all n by 4 times, you will get n steps. So you can see at each level, when we have just draw this calling structure, recursive call structure. Each level, our total number of steps is fixed n. So how many levels will be there total?
Log base to n.
So you can see initially first call we have n, next level call n by 2, next level call is n by 4, next is n by 8. So in this way means every time we are dividing by 2. So total log n levels you will reach at the base case t1. Okay, and each level you have n steps. Okay, so log n levels are there, each level has n steps, so n into log n. Total steps.
Sir, I understood the recursive relation. How did you get the tree from the recursive relation, sir?
So this is the calling tree. We have, so initially Tn is the main call. Tn is the total time.
Yes, sir.
But we have written like 2Tn by 2 plus n time for merge function. Okay.
Yes, sir.
So we have just draw the structure only in the recursive call. So Tn
Yes,
is the first call, but from this we call 2 times this Tn by 2, Tn by 2.
And we also, sir, we also do plus n, no, sir?
Plus n. So that plus n by 2 you can write here, n by 2 plus n by 2.
Yes, sir.
And plus n you can write. Okay, so because of that mention, because this n by 2 is coming in the bottom of approach. Like if you have a list like this, a merge sort list like 4, 3, 8, 2, 1, 6, 5, 9. If you want to give suppose if you have this unordered list, so what is how merge actually works? So that breaks the list first. Okay, so like 4, 3, 8, 2, and another list you will get like 6, 5. Sorry, 1, 1, 6, 5, 9. So still this contains more than one element. Again, it will break into two sides. So 4 and 3, then 8, 2, and it will again break like this. So 1, 6, and 5, 9. Okay. So this is the first initial breaking steps. Still, it is contains more than one element. So now again break into the single element. 4, now 3, and again it break like this. 8, 2, same 1, and 6, and 5, and 9. Okay. Like this. So once we reached at the list with one element, so one element we can consider as a sorted element. Okay, sorted list. So if we have only one element in the list, we can consider as a sorted list. Now we can combine two sorted lists into a one sorted list with the help of merge function. So merge function is basically takes two sorted lists and combine into a one sorted list. So that means now the merge process is start from this level. So this will merge. Okay, so like this will merge, and this will now it become a 4, 3, 4, like this. Now this part will merge. Okay, merge will happen. So 2, 8, 2, 12. Now 1, 6, and 5, 9. So now merging is happening like this. Okay, so this merge is happening from the bottom to up approach like this. So again, now we have two sorted list, and this merge like 2, 3, 4, and 8. Okay, now these are two sorted list. This will merge into a one sorted list. So 1, 5, 6, 9. Now you got two sorted list this one, and merge will happen for these two. So now you will get a total sorted 1, 2, 3, 4, and 5, 6, 8, 9. Okay, so that means merge operation for the initial part when we call this function merge. So this will come up back to the sorted list, like here sorted, then this sorted, and then we'll merge into a final sorted. So this n is coming when we are getting the two sorted list from the lower part and merging them. Okay, so this n is coming from here. So now we can consider like write like this t n by 2 plus n by 2. Same for the second call. So this level n steps are there. Second level, if you will add both, so that is n again, n by 2 plus n by 2 n. Next level, there are again two to call from both. So t n by 4, t n by 4, t n by 4, t n by 4. Okay. So again, merge steps take n by 4 at each call. N by 4. Add both all 4. So n by 4 multiply 4. So n again. So next time 8 into n by 8. Again n. So in this way, this will extend to till t1. Okay, so that means t1 are last level. So total 1 plus 1 till still n. So total log n levels are there because every time you can see n, then n by 2, n by 4. This is you will reach at the t1 in log n steps. So that means log n levels are there. Each level contains this part of n steps. So log n levels and n steps at each level. So n into log n total steps. So this is the complexity for merge function, merge sort complexity, and this is the recurrence relation for that. Okay, so this type of recurrence relation. Another way is also there, like so this recurrence tree is covered in our course. One master theorem is also there. So master theorem like works Tn. Let me just little bit explain to you. So Tn.
Sir, before that, like, could you solve that mathematical way of getting that n log n also?
As I mentioned that every equation we cannot come up with mathematical expression to just represent easily complexity. So we can use another method also. Okay.
Okay.
So
why? Because if it is 2 every time is added, no, sir. Like then it will be n 2 to the power n by 2. Like that form will come, right?
So that you have come up with some relative information. So I am not much like this mathematical things. I am not much comfortable. So what equation we will get if you expand this? You have to come up some idea that like that what type of expression you are getting and how you can solve mathematically that. Okay. Some expression you can easily identify that, but some expression will become more complex.
Okay. Okay.
So because of that, multiple ways are available to calculate the complexity. One is that master theorem. So that is written like this. So Tn equal to so this A T n by B plus Fn. So every recurrence relation written in this form in the recurrence relation. So where A is the how many times we are calling the recurrence function, B is how we are dividing our input in the each call, and Fn is represent the additional time by the function. So if we can compare this recurrence relation, so like previous Tn equal to 2 Tn by 2 plus n. So you can relate this A equal to 2, B equal to 2, Fn equal to n. Like you can identify this. After that, we compare this. So we calculate the terms log BA. Okay, so b base and a value. So we calculate this log b a value as a k.
So A, B are coefficients.
This is not a coefficient. This is representing some information. So how many times we are calling the recurrence function, recursive function. So that is representing by a. Okay, and this b is representing how we are dividing our input in each recursive call by which value. So this is here you can see we are dividing our input n by 2 each time. So this 2 become a b value.
Relation.
So we are just, this is the master theorem expression. So we relate our recurrence relation to this expression and we identified the value of a, b and fn. What is our a, b and fn value in our recurrence relation? Okay, by in this way. So a value is representing this number of call. B value is representing this how we are dividing our n input in recursive call. Fn value is representing the additional steps. So this. After getting this information, we calculate this k equal to log ba. Okay. Now we compare our fn. We compare our fn with this k value, or not this k, n to the power this k. N to the power k. We can see this k. We compare this fn with n to the power k. So if we are getting this n to the power k greater or smaller or equal, based on that we can identify the complexity. So case 1 we have like case 1 we can understand that when we compare this. So first we will calculate this log ba value. Okay. So log ba value you can calculate like this log here for a equal to 2, b equal to 2. So base, this b is equal to now become base and this a become a value. So 2, 2. Okay. So this value is now a this fn is equal to n. And now just put this n to the power log 2, 2. So this become a 1, correct? So if you consider this n to the power, so this become a n. So now we calculate this n to the power k. This is n. Fn is also n. So there is multiple case. We have total 3 cases actually. If our fn is smaller than n to the power k. Okay, this is the case 1. So in this case, how we will write our complexity? So if you are getting this situation, fn is less than n to the power k, you can write your complexity like tn equal to big O n to the power k. This will become a direct complexity if you are getting this situation. If you are getting case 2, when fn equal to n to the power k, both are same. So you can write the complexity tn equal to fn, this big O, fn into this. So a second, where it is? Fn equal to log n. You can directly retain this complexity if your second condition is matched, case 2. Okay, so fn into log n. And if case 3 is just if your fn is greater than n to the power k. So you can write your complexity tn equal to big O fn. This is the master theorem which we have directly. So after putting all these values in this relation, just calculate, just compare fn and n to the power k. So if you are getting less than, you can directly write your complexity like this: fn equal to big O n to the power k. If you are getting both equal, you can write complexity ft, this tn equal to big O fn into log n. Okay, and this is the case 3. If you are getting fn is greater than n to the power k, so that tn equal to big O fn directly you can put. So this is the direct master theorem you can apply. This is not covered in the course, so but additionally you can explore this master theorem. But recurrence relation is also the similar type of things where we also identified the complexity. Actually, here you can see if we are getting at each step same, okay, same operation. So we will directly write the complexity like fn equal to log n. This complexity. If these steps are increasing by some factor continuously, so that is the case when we write the complexity n to the power log Same B is this one or like this B A, that you can directly write the complexity like this. If these steps are decreasing by some factor, then we write the complexity directly f this big O f n, this order of n, by this recurrence relation. Okay, so this is some way to identify the complexity for this recurrence relation. So either you can use this recursion tree or you can use this master theorem to calculate. Recursion tree is discussed in Week-8 later, so you will see. But I have already discussed some idea for both. Okay, so you can explore these. Yeah, any doubt in this? Yeah, this is a little bit new things. So maybe after some practice, you will get some clear idea.
Sir, for which kind of code that is the n bar log here basically?
Which case? Okay, this n to the power log b. So case when you are drawing this tree structure, recursion tree, okay, recursion tree structure, and each steps you are getting, your steps are increasing. Suppose one recurrence relation we have like this. So Tn equal to 2, not 2, okay, so 4, like 4 T n by 2 plus n, like this. Okay, suppose this recurrence relation is there. So for any algorithm, so now what will happen? So Tn is the first call. Okay, now after that you have 4 call. Okay, Tn by 2, Tn by 2, Tn by 2, Tn by 2. Okay, at each steps you have also additional n steps. So here n is there, but next step n plus 2 plus n plus 2 plus n plus 2 plus n plus 2. Okay, 4 times. So 4 into n by 2. So that is 2n. Okay, next time each call have 4 call with n by 4 like this. So that means 16 into n by 4. That become 4n. So here you can write 2 to the power 0n, 2 to the power 1n, here 2 to the power 2n. So you can see each steps your this is are increasing actually. Total steps are increasing. So in this way you can calculate the complexity like Tn equal to big O n to the power log Ba. Okay, so B is this value and A is this value. Okay, so what is this? So big O n log B is now 2 base 2 and this is 4. Okay, so 4 we can write 2 to the power 2. 2 will come here, so that will become so big O n square. Okay, log 2 base 2 value will become equal to 1. So that is now complexity for this recurrence. Okay, so we can directly come up with this complexity by this method. So these are the recurrence relation how we can solve. If you are getting reducing, so at that time directly pick the fn part and represent with the complexity.
Yes, sir. Are these theorems uploaded in the notebook?
Which one? This no. So this master theorem is not added. This is not the part of syllabus. So I've just additionally explained this. You can explore. Okay, that is also used to calculate the complexity for recursive functions. But in our course, we use this recursion tree approach in Week-8.
This is used only recursive.
This recursion tree is also used to calculate the complexity for recursive function. Okay.
So this, where we just have given the theorem, thereby, like we have to learn this or we have to skip that?
Master theorem, you can skip that, but this is you can explore because this time complexity calculation, it is just like a future, like if you are giving any gate exam or any type of this exam, you should know multiple way to calculate the complexity. Okay, so recursion tree is this.
The we go.
Big O notation you can use to represent the complexity. So always use big O. Okay, don't confuse too much in big O and theta, all these things. Okay, so just come up with only big O things. So what your question here? Can you repeat again?
No need, sir, for it.
Okay. So now these are the complexity part. Okay, so you can again BK you will discuss in recursion tree again. Okay, but meanwhile you can explore both method. This recursion tree or will also use again if required. So now next thing is searching algorithm. So naive approach, definitely this is very easy. I think no need to discuss. So we simply compare each element one by one and identify that that we have the elements exist or not. And this is simply a one linear loop and complexity for this order of n. Okay, so this is the worst case, average case. But the best case, we can get our searching element in order of n one time. So average case is some place you will see n by 2, but generally we not use the terms two things or these things constant term. So we always use order of this n parts. Okay, so we remove that. That is also considered as the order of big O n. Binary search, yeah. If you know this binary search things algorithm, so what is the prerequisite for the binary search? Can you tell me?
Sir, it should be sorted, sir.
It should be sorted. Yeah. So a standard binary search algorithm require the sorted input. Okay, then it can be applied only. So the logic is simple.
Sorry, sir, but for my case, linear search, I don't know.
Oh, linear search you don't know? Okay. So linear search is simple code. If you have simple any list like 3, 5, 4, 2, 1, 8, 6, 9, like this. 11. So linear search, your input may be in any order, okay, an order or like any order. So the way to identify if you are searching any element like 9, how you will do this? How you will search this 9 is exist in this list or not? This is the simple logic actually. What you will do? So you can identify it by simple comparisons. So start from the first index, 0 index for the list, and start comparison. So this first index element is matched with our searching element or not. If not, move to the next index. Okay, like this, and compare again. And then again, if it is not matched, then compare again. Okay, so this just repeat this process until you will not reach at the your searching element. So repeat this process. Once you will reach at this point, you will get your searching element is matched with here, or you will return the result that it is exist, or maybe you will return the index for it. So this is the linear way. You are traversing each element one by one and comparing it with the searching element and coming up with the result or your output. Okay. So if you see the implementation for this is simply one linear loop. Okay, linear like this. Naive search, you have this one loop for I range L, and you are comparing your searching element V with each element. Return I if it is matched, okay, equal, and return false. If this loop is terminated without returning anything, you will return false. Okay, that means your element is not exist. So this is single iterative loop. It will take worst time if your element exists at the last position. If it will take least time if your element exists at the first position. That is a constant operation. Best case. Worst case is order of n. Okay, average cases now all possible case in between. So that is n by 2, but we will represent only n part. The constant part we will remove. So this is the linear search. Binary search, we need a sorted list, because if this is list is sorted, then we can identify that which part we need to search again. Okay, so suppose we have our input list like this, 1, 5, 8, 10, 11, 12, 14, 20, 30, 35 like this, okay, and you are searching something like 30 element, it is exist or not. So this is sorted list. What you can do, you can just check the middle element. So how many elements you have? 1 2 3 4 5 6 7 8 9 10 11. Okay, so 0 and 10 is the index. 0 is the first index, 10 is the last index. So you can just use this index, you can identify the middle index by just adding low index plus high index and divide by 2. So 0 plus 10, okay, 0 plus 10 and divide by 2. So 10 floor division 2, you will get 5. So that means directly check the fifth index. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Directly check this fifth index. Just calculate the middle index and check directly. And compare this. Your searching element is 30. 30 is equal to 12? No. Now 30 is greater than to the 12. So that means this 30 will only come after this 12, not before this. So just remove this part for checking, okay? Just only consider the remaining part, half part. So that means we have removed half of the searching area at the one step. So next step, now your first element with index 6 and last index is 10. So 6 plus 10 and divided by 2. Okay, so you will get an 8 index. So now just check the middle element for this part only. So 8 index, you can see 30. We got matched. Okay, so in this way, just apply this process repeatedly. So this is also the same things. Initially, you have the n input to search. In the next step, you only remaining n by 2 elements to search. Next time n by 4. In this way, you will list at the one element in log n step. Okay, log n steps, you will list at the one step, and if that is also not matched, so that means your element is not exist. So in this way, you can discard half of the searching area every time, and you can identify the element in log n steps. So that is very fast search, and if you have suppose 1024 these number of elements, you can search any element which is exist at any place in only 10 steps, 10 comparison. Okay, but in the linear search, if you will apply, so in the worst case situation, maybe 1024 comparisons is required. But in this case, only 10. But the condition is required, your data should be sorted. Maybe it may be either in increasing order or decreasing order, like I said. Okay, so standard binary search work like this. And complexity, as we have seen, total log n comparison is required, so log n complexity for this. Or so this is also can be written as the recursive function. So we can also write the recurrence relation for this. So that recurrence relation will look like this: t n by 2 and plus 1. Only this will be the recurrence relation. So initially we have this call, and next time we are only checking for the half element, and each time we are only comparing the middle element one step. Okay, so that is the recurrence relation. Okay, so now this is because so one important point we have mentioned in the notes also, when you are implementing binary search. Okay, so some questions are also there, some variant of this binary search. Do not use slicing in this implementation. Okay, here you can see this implementation is given on this while loop process. We are not using slicing anywhere, but some recursive implementation. So I think this implementation also used in the lecture. Okay, Python actually provides some shortcut things, but internally that also performs some operation. Okay, so this slicing actually which we are using here. So this operation internally take order of n steps. Okay, so if you are writing this slicing here, so what we are doing actually, so this is a recursive function, and we are passing half of the list. If our element is smaller, then we are passing half of the initial list. Okay, by slicing method. But this is actually not a, we are passing the same list. We are just passing the copy of the half of the list. So if we have total L list with n element, okay, so we have total n elements. Now, when we are passing into the function this using the slicing, so what happening? One new copy is creating. That means new object is creating with half of the element. So like initial half. So that means n by 2. this index. So that means all elements are copying from this main list to the new list. So n by 2 elements are copied. So this copy steps are performing n by 2 steps. Okay, and this become order of n complexity. So this operation internally is taking order of n time. This is slicing operation. And binary search, our goal is to achieve log n time. Okay, so if any operation is taking order of a time, then it will become a complexity for this. And this is totally equivalent to the linear search order of n. So then there is no benefit for this binary search. Okay, so due to this slicing operation, which internally takes some operation, perform some operation, if you trying to compare your binary search with this slicing with the linear search, you will get approx similar time. So when you are trying to achieve log n complexity, okay, so do not use slicing implementation. Instead of slicing, you can use the different way to write the same recursive implementation with the help of index parameter. So that we have added here. So without slicing, you can see this is the also a binary search. But here this time we are not using slicing part. Instead of slicing, we are passing the same object L. But we are mentioning what is the starting index and what is the last index to search next same list by 2 parameters. Okay. So next time we will only use this index to search the area. Okay, starting index to bit -1. So this is the another variant of recursive implementation. So now in this way, this is the log n time. Practically, it will perform log n. Okay. So now this is binary search. Now sorting algorithms comes. So sorting algorithms, we have multiple algorithms. First is selection sort. So anyone can tell me what is the concept of selection sort?
So we take a list, and every time we take a minimum list and append to the new list.
Okay.
And then every time we take a minimum list, we remove it from the original list, or else we'll swap the minimum list position with the with its position.
Okay, you got the point. So to selection sort, this is also a superset of one another problem. Like do you know how to identify the minimum element in any list? This is the sub problem. Identify the maximum element or identify the minimum element in the list. How you will do this operation? Simply comparison.
Yes, sir.
Okay, so suppose if you have any unsorted list like 3, 4, 5, 6, 2, 8, 9, like this. So how you will identify the minimum element in this list? So simply what you can do, you can assume that first element is the smallest element. Okay, and after that compare each element. If you find smaller element compared to the previous minimum element, then replace it. Okay, just make the new element as the smallest element. So just do the process, compare each element one by one. Suppose if m equal to now 3. Okay, now we will compare this 4 is smaller than 3, no. 5 is smaller than 3, no. 6 is smaller than 3, no. 2 is smaller than 3, yes. So now we will update our m equal to 2. This is the minimum element. Now we will compare again. So 8 is smaller than 2, no. 9 is smaller than 2, no. So finally, after comparing each element, what is the last updated value for m? This is 2. That means 2 is the smallest element in this. So this is the one part you should know for the selection sort. Now for the selection sort, what we are doing? We are looking the smallest element for each location. So that means initially for first location, because in the sorted list, what happened actually, we have at the first position, first smallest element should come. For the second position, second smallest element should come, like this. Okay. So the same concept we are using here. For the first location, we are finding out the smallest element in this part. 3 total all elements. Okay. After getting the all smallest element, we will just swap the smallest element with the first location. Okay. So after first iteration, you will get 2 at the first, and now 4, 5, 6, 3, 8, 9. Now this is the smallest element we got. Now ignore it. Okay, this position. Now we will look for the second smallest element. Or you can consider that in this part. Again find the smallest element. Only this part. Just do not consider this previous part. Same things, do the same process again. Identify the smallest element in this part, remaining part. So same thing again we will repeat. We will consider that this is the smallest, and we will compare again and identify the smallest element in this part. Now 3 is the smallest in this part. So we will swap this with this position. Okay, now 2 and 3, and now 5, 6, and 4, and 8, and 9. Now we will repeat the same process for the remaining part. Again identify the smallest element for this first element position. Okay, so this process we are already repeating. So that means for each position we are identifying the smallest element in the remaining unsorted part.
Sir,
Yes.
why are we concerned with doing this operation in place? Why can't we take a new list and every time put them in?
So again, same thing. If we can do in place, why we are increasing the space complexity? We are not covering. We are not covering space complexity in this. But additionally, if you are taking additional space, so that increase your space complexity. If you can do the.
Sir, in this case, if two similar number appears,
So in this case, again, two similar numbers are there. Suppose 2 is repeating 2 times. Just pick any one of them. Another one will come for the second position.
no, sir. If the array will have 2, then again a second number 2, it will search.
No, this is not a searching. This is sorting.
Yeah, sorting, sir. Like how? Like, could you please throw up?
So again, same things. Suppose if you have list and where the elements are repeated. Suppose in this list, this 2 is existing, and again here 2 is existing again here. So still, if you are looking the smallest element, you will get 2 now. Because when you are comparing the minimum, initially m equal to 3. Okay, once you find 2, then you will update m equal to 2. Then again, if you find 2, so you will not update this, because you are only updating if you are getting a smaller element, not the equal element. So this 2 will remain same. So in the first time, any one of these 2 will come at the first place, or this will replace here like this. So this is depends on the algorithm implementation or algorithm. When you are finding the minimum element, are you replacing the element if you are finding the same element or not in your implementation? Okay.
Sir,
here,
so finding the minimum element from the list, is it taking the worst case of order of n complexity? So we are doing for each and every position. So this algorithm is taking order of n square complexity. Am I right? Oh, okay, okay.
Yes, you are right.
Got the touch really high.
But we will come up with the expression how we are calculating the complexity for this. So if you have multiple, so this concept is called as a stability. Okay, stable algorithm or not. If you have similar element in your input list, so are the similar element order is changed or not in the sorted output? So that is called the stability properties of the algorithm. So if your algorithm is changing the position of similar elements in the output list, then that algorithm is not stable algorithm. If your algorithm is not changing the position of same algorithm, means order. Suppose let me give the example of stability thing.
Sir, I'm not getting that, sir. What is that stability?
Stability.
So stability, you mean if you are changing the? I am not understanding, sir. Please explain.
Yeah, just example 4, 3, 5, 2, 6, 2. Suppose this is the input list. Okay. Now there are repeated element like this. This is one, first two. This is second two. Correct?
Yes. Yes, sir.
If I am so this is the same value actually. This is the same value. The final output we will get like this. Okay, so 2, 2, 3, 4, 5,
5, 6,
6,
8.
8. Correct?
Yes,
But
sir.
these two, if I just give the name like this is the A and this is the B, so are we getting the same order? This A is coming first and B is coming second.
Sir, same order in the sense like A is first and B is second. That order you are asking?
Yes. So
Or index?
here I am just giving the name first occurrence of this two where I am just giving the name A. Okay, second occurrence of this two I am giving the name B. So this this order should remain same in the sorted output.
Okay.
If our algorithm is guaranteed this property, these features, then our algorithm is called as a stable algorithm. If our algorithms may change the order, like this 2, 2, 3, 4, 5,
5,
6,
6,
8,
8.
but
B
this
comes.
is now B and this is A.
Right, right.
Okay, then this is not a stable algorithm. Okay, this is for this type of data we are not able to we are not figuring out that what is the effect of this if we are changing the order. But some like database if you are using we have the group data, okay, and we are maintaining some rank. Okay, so based on that some like we have some student ID, okay, ID first and then age and then score. Okay, some exam maintain this type of ranking. So age, if score is same, okay, so suppose we are giving this this data ID and age, where the age is in increasing order, okay, like 20, 20, 30, like this 40 in this way. But now we are just maintaining our this list based on the score. Okay, now we have the all score, and we want to sort this list based on the score. Okay, but if score is same, then our data should be remain sorted based on the age, because our input this ID and age was sorted based on the age. Now we have put all the scores. Now we want to sort this complete data based on score. But if score is same, then our data should remain the sorted according to the age. So that means here this stability is required.
Got it, sir.
Okay. So because of that, this is important features for the sorting algorithm.
Opposite then?
Opposite means? So this if this order, so descending, that is the requirement, what type of requirement we have. Okay, so that means stability is only focused on the similar value elements. That order of the similar element, if it is changing, then algorithm is not stable. If it is not changing, then our algorithm is stable.
No, but what we need to change for this? Like, what is the element that need to be changed for descending?
Then algorithm you have to change completely. Your algorithm you have to make to like in descending order. So this is again you are sorting the algorithm, but your algorithm is now you want into the descending order. So some you can in the sorting algorithm you can also compare two parameters at the same time. And we are just talking about the standard sorting algorithms. Okay, what we have this selection sort, insertion sort. But if you have different purpose, like in the different you want to sort this list based on the two parameter, then you can modify your sort. Okay, if your value is like this score value is same, then just take the highest, just compare the age, and then pick the highest age first and lowest is later. Then you can apply the another logic. But standard algorithm is by default stable or not. We are talking for that. Okay, so selection sort is not stable.
Sir, how do we know, sir, from the result that it has changed the index?
So sorry, how?
How do we know from the result after sorting out that this is changed or indexes are
Order
changed.
or not? Order. So how do you know? Yeah. So this is the actually properties of the selection sort. So how we can, like, you can come up with counter example by the process. So let me just tell you to prove this how selection sort actually is not stable. Okay. So suppose you have one input. So you know the selection sort way, how we are calculating the sort this thing, how we are sorting the that. Okay. So how this actually change the order? Suppose you have the input like one second, okay, so four, three, okay. So you can see, suppose this input list we have. How selection sort will work for this? Now here a similar element is 3. Okay, I'm just giving the name A and this B. Okay. Now selection sort what will do? It will identify the smallest element for this position. So what will be the element? 1.
Yes.
Now swap will happen. This A element will swap with this one. Okay, so now what will happen? 1, 4, 3. This is B, and now this is 2, and this will come here. Okay, so 3A. Now for second position, you can see this element will replace this, and you will get 1 and 2 and 3B
3B, 4,
and 4
3.
and then 3. Okay. Now for this position, you can see this is the shortest actually. This is the smallest. This will remain at the same place. And again, for this is the smallest. So this will replace here only.
Yes.
So this 1, 2, 3B
3B,
and 3A
4.
and 4. Okay. So in this way, you can see this order is now changed.
Order is changed, sir.
So selection sort main standard algorithm may change the order. So because of that, this is not stable, but this is in place. Okay. So this type of property you can also remember for the exam. Okay, so selection sort. Now complexity part here. So as you can see in the first step, when we are looking the smallest element for first location, this location. So we are comparing all the remaining element, okay, and we are getting the total of identifying the first smallest element. So that means total n steps we are taking for the first time. But after getting the smallest element here, as you can see, we have reduced the size of problem. Now we are looking the smallest element for this part, and we have now n minus 1 elements.
N minus 1.
So next step, n minus 1 step is required. Next time, only these elements are remaining. So this is n minus 2. So in this way, each time your steps are decreasing. So you are getting n plus n minus 1, okay, plus n minus 2, plus like this 2, 1. If you will add this series, you will get n into n plus 1.
N plus 1 by 2, so n square.
If you multiply this, so n is square by 2 plus n by 2. Okay, so this is the highest order. And remove this constant, so the order of n is square. The complexity for this. Okay. So this algorithms is actually not, total number of steps are not changed based on any order of input. Okay. So if you pass the complete sorted list also for this algorithm, 1, 2, 3, 4, 5, still it will perform your full task. Okay. So for this part, again, it will also compare each element and come up with all this no swap with it. Okay. And this. So total, still the same number of steps will be there. Because of that, each type of case we can consider that this always take order of n square. Each situation. So you can consider the best case, worst case, always it will take order of n square steps.
Right.
Okay, so insertion sort. Yeah, insertion sort concept is you have some elements, like I'm just giving the basic idea. You have some sorted list. Suppose if you have some sorted part like 3, 6, 8, 10 like this. This is the sorted part you have. Now one new element is coming from this side. Okay, one new element is coming. You have one already sorted list. Now one new element is coming like 4. Just how you will insert that into a correct position to make sorted again. Okay, so what you can do, you can just compare with the last element, this new element which you are coming from this side, compare with this 10. If this is not in correct order, then compare with this next element. Okay, so again this is not in the correct order, so again compare with this 6. So this is again, but now when you compare this 3, so now this is in the correct order. Okay, so 3 and 4, so that means 3 is smaller than. So once you find out the position where you should insert, so insert that place. So that's 6 was greater than 4, so you move to the third, but third is smaller than. So just stop the process and insert that point 4. So now it will become again sorted. So 3, 4, 6, 8, 10. Now suppose if you are inserting like 7, so how much steps are required to insert this at the correct position by this way? So you will compare with 10 and 7 not in correct order. Now compare with the previous next element. So 8 is still greater than 7. Now compare with this 6. So now 6 is smaller than this. And insert this after this 6. Okay, 7.
Sir,
So this
I have a
previous
doubt.
comparison is not required.
Sir, I have a doubt here. Like, so we are comparing this element from last, and if it is not before. So why it is not comparing like binary search? For example, 7. We are finding the middle value. Why? Because it is already sorted. So I will compare 6 with 7. If it is greater, then I will find the middle value like that thing.
So you are saying you want to apply the binary search in the previous part.
Like, yeah, for this inserting, finding the index for this inserting, instead of this from left right to going linearly, why not we are doing that binary search like that?
You can do. So this is just an example. So we are just assuming that we have the sorted list initially, and we are inserting. To insert the element at the correct position, you can apply. If you have sorted list, you can insert in this way. But the logic of insertion sort is different. Okay, that is a standard algorithm that follow the something. But you can write your approach also to do something. Okay, that. So standard algorithm for insertion sort is the use this concept actually.
Okay.
Okay, but if you have different way, definitely we have, because of that we have multiple different algorithms for this sorting. We have already seen selection sort. Now we are looking in insertion sort. So this is just like a research things. So time to time, so we got some new algorithms which more efficiency. So we got that algorithm. So because of that, we are looking multiple algorithms for the same task. Okay, and some have some advantage over to the another algorithm. So like we see advantage for insertion sort also. So the approach of this insertion sort is like this: we have some previous sorted part, and we are inserting a new element like this.
Okay.
By comparing, okay,
yes,
with the previous element and inserting into the correct position. So so always we will get the one sorted part, and we are picking the one element from the unsorted part, and we are inserting into the sorted part. So this approach we are using in the insertion sort algorithm, and that is the logic behind the insertion sort. So you can see this.
Sir, if you are getting 7 in the middle, sir, then we will put before 7 or after 7, sir?
After 7. Suppose we have duplicate element, so we only move if we are getting bigger element before that. If we are getting the same element, we will insert after that. So you can see this approach here, what we are doing in the same way. So this is the base case. We are assuming that if we have only empty list, we will directly get done, but this is the main part. So for I in range n, okay, so for each element we will try this. So j equal to I, while j, so this is the starting point actually where we are just looking. So initially j is suppose we have element like this, 5 and 4, 1, 3, 8, 2, 7, like this. Okay. So what we are looking, we are starting from this position, and we are looking. So j equal to I. We are looking any previous part we have for this. So j is greater than. So this while loop, this is running. You can see. So we are starting j equal to I. I is started from 0. Or we can also modify this. We can start from this second element, because if one element is always a sorted element. Okay, so we can also start with second element directly from in this algorithm. So this is only one step change, so that will not affect the complexity or something, but some minor change you can do also. So while j is greater than equal to 0, so this is the condition for terminate, and Lj is smaller than Lj minus 1. Okay, so that means we are comparing the current element with the previous element. If that is not in the correct order, we are swapping. Okay, we are swapping the position. So that means we are comparing 5, but there is no 5. So this you can see j is greater than 0. But in the first case, j is equal to I. So j I is 0, so j 0. So this first iteration will not run by this condition to terminate. Now in the second iteration, I become 1. So now I equal to 1. So that means we are looking this element 4. Now I is j is greater than 0 because j is now 1, and we are checking this 4 is smaller than this previous element Lj minus 1. If this is the condition, okay, so 4 is smaller than 5. So that means this is not in correct order. This pair is not in the correct order. So we will swap the position. But we will repeat this process until we will, if we are getting the same things. Once we will get this condition not correct, we will stop the process. Okay. So now in the first step, 4 is smaller than 5. So we will swap this process. Okay. So 4 is now coming at this position. 4 and 5. Now our j is reduced 1, so j is become 0. So this loop will terminate at this step. Now we are looking this 1. Okay, 1. Now 1 is less than 5. Yes, so this will swap. So there is different implementation is available. What happens sometimes we will not swap at every steps. We will identify the steps finally, and we will swap at the last point. Okay. So what can happen where we can swap this? Some shifting also we will perform. Actually, we copy this element at some element like k equal to 1. Okay. After that, if we check if this element is smaller than the previous element, what we will do, we will just shift this element here. Okay. 4. Again, we will check if this k is smaller than 5. If yes, we will shift into the next position. Okay. So in this way, we will shift our element. Once we will get the situation where our element is not smaller than, then we will paste this value at that position. So this way you can also use. Otherwise, swap method you can also do by this way. So in this way, so previous part you can see 4 and 5. Now we are inserting new element into this. So where this should insert? So 1 and 5 not in correct order, 5, 1. Okay. So again 1 and 4 not in correct order. So again swap. Now our list is finished. Okay. So 1, 4, 5. Okay. Now we will pick the next element and we will check. 3 is smaller than 5. Swap. Okay. So 5, 3. Now 3 change with this 4. Yeah, still not in correct order. Swap this. But here this is correct order. So our 3 will shift like this. So first 3, 5, then 4, 3, 3, 4 like this. Okay. So 1, 3, 4, 5. So how you can insert? What approach you can apply to insert in this way? You can also modify your code. Okay. So this is written here. You can also apply your approach. Yeah. So that is also a insertion sort. Yeah.
Why can't we do this with for loop itself? We can.
You can use this
each element and checking.
As I mentioned that, what is the concept of insertion sort? Concept is just compare, just insert at the correct position by just comparing. Okay. So just do the same process by you can use for loop also. You can start with the previous element and just compare each element where you are just getting the correct position. Just insert and break your loop. Okay. So you can also apply this implementation. So as I mentioned, just pick the current element and insert into a previous sorted part at the correct position by comparing. Okay, element 1 by 1.
Sir,
So
what
this
is sir? What is the advantage of this? Sir?
so advantage. So this is just a one different approach to sort the algorithm. Okay. So every time we are just inserting the new element into the previous sorted elements, and our list is now becoming sorted. Okay. So we are getting finally sorted output from this. So if we talk about why this insertion sort is good and which type of case this is good. So best case, if you see the complexity best case, this algorithm takes order of n time. Why this it takes order of n time? Because if you see, if you already getting sorted input, okay, 1 2 3 4 5 6 like this, already getting sorted input, you are passing to sorted input to the insertion sort. Selection sort will perform order of n square steps, but insertion sort will stop every time only by comparing the last element. So in the first iteration, so 1 is there. When you will take the 2, so you will only compare with the previous element, and you see this is already in correct order. So you will not compare with the all previous element. So at this means this while loop will run only one time for each steps or for each value of I. Okay, so
Yes.
now 2. Now 3, when you are inserting 3, you will only compare with the last 2. Then you will see this is a smaller element. So that means this 3 should come after this. Okay, so only one step you will stop. 1 2 3. Same 4 step you will compare only 3. Then you will see this is already smaller. So again 4 you will insert here. So every time for each element you are only comparing one time. So total time n steps is required to return this output or sorted order. So that means this algorithm takes order of n steps in best case situation if your or input is already approx sorted. Okay. So this is the best advantage, and this is the advantage for insertion sort. So for this already sorted element, you will get order of n time by this algorithm. But other case like worst case situation, that is the totally different thing. So this algorithm will also take the same steps as selection sort. So worst case is situation when you are in reverse order. Okay, like 6 5 3 4 2 1 like this. Okay. So for first location 6 is now sorted. Okay. Now when you're taking 5, this will compare with this 6 and order will be changed. So 5 and 6. Now 3 will compare with both. Okay. And then you will get 3 5 6. Now 4 will compare all 3. Okay, so you can see first step we compare, there was no comparison, one step only. Okay, second time two steps, and third time 3 steps. So in this way steps are increasing at every element. Okay, so now 2 will compare all with this 3. Sorry, 4 will compare all with this 3. So 3 4 5. Oh, no, we have written back. So this 3 will come, 3 4 5 6, and 2 will come after comparison of with all 4 elements. So then you will get 2 3 4 5 6. Now 1 will compare with every element. Okay, so in this way you are getting like this: one step at the first element, 2 steps for the second, 3 steps for the third element. In this way, total n steps for the last element. So same type of order you are getting, and you are getting the same n into n plus 1 by 2 n square for this. Okay, so this is the worst case, and average case also have the same order of n square. Okay. Now merge sort is the another approach. So that sort I've already discussed the thing. This thing. So merge sort actually use the divide and conquer approach. So it first divide the problem into the smaller problem. Okay, and after that it divide and conquer. So that means it combine the solution of sub problems. So that means this is the like a recursive process, and so as I mentioned that how it works. So again, so the concept when this is recursively we first divide the list. So for 8, 1, 3, 6, 2, 5, 9, like this. So first, this is the initial list. First, it breaks into two. Okay, 4, 8, 1, 3, and 6, 2, 5, 9. Again, it breaks into two. So this is the recursive process. Okay. So every time we will divide this if we have the more than one size of the list. 4, 8, and 1, 3, 6, 2, and 5, 9. Okay. So this is the part. Again, still we have more than one size. So again, it will breaks into two. So like 4, 8, and 1 and 3. Now 6 and 2 and 5 and 9. So recursively, our algorithm is dividing into the half again and again, and it is reaching to the one element. Because now we will use the approach of merging two sorted lists. So because single element is considered as a sorted element. So now this is sorted, this is sorted. Now we will start the merge process. So this is the divide process. Now combine the solution. Okay, merge process. So 4 and 8 we are just taking two sorted lists and we are combining into a one sorted list. That is why merge operation. So merge operation, I hope you know how merge operation performs. So let me show you merge operation. Okay. So for merge operation, so suppose we have sorted list, like I am taking the different place. So like 2, 3, 6, 8. This is the one sorted list, and 5, 9, 10, 12. This is the another sorted list. This is the A and this is the B. This list. So we takes index I equal to at the first element, j equal to first element, and we take the final merge list. So we maintain this final merge sorted list. So we compare each element with this correspond to the I and j, and compare which one is the smaller, that will move to the final sorted list. Okay. So like 2 and 5, 2 is smaller, 2 will move here. Now which element which we are moving from the list, that pointer will move to the next element. Okay. So here this I will move to the next element. Now again compare I and j position. So 3 and 5, which one is smaller? So again I. So this 3 will come here. So this point index will move to the next. So 6 and 5, which one is smaller? Now j. So 5 will come here. J will move. Okay. So now 6 and 9, which one is smaller? So this I. So 6 will come here. Okay. So I will move here. 8 and 9, again 8 is smaller. So now once any list is completed, all the remaining element from the second element will directly insert. Okay. So 9, 10, 11. So in this way, this merge function actually works. Combine two sorted lists into a one sorted list. So we are doing this process
Sir,
here.
sir. In that third item is 4. A third item is 4. Yes,
Okay.
sir, that 4. So how it will go, sir?
Okay. So 2 is the first element, then 3 is the first element, then 4 is the smaller than 5. So 4 will come.
Oh, yes, sir, yes.
Okay, 4 will come. Then it will move 8. So now 5 will come. Okay, and now 8 will come. 8 will come. And now remaining elements are all remaining elements. Okay. So now sorting, merging is happening like this. So we are getting to sorted list 4 and 8, and we will merge this into, and we will get the sorted list 4, 8. Again here 1 and 3. Here we will get 2 and 6. Here we will get 5 and 9. Okay. So we will repeat the same process again. So this is again now merging two sorted lists. So 1, 3, 4, and 8.
This has been already discussed.
This is already discussed, but I'll just repeat it.
That's all.
I have discussed that at the time of time complexity things. So 2, 5, 6, 9. Okay. Again, we have two sorted lists. We will get final sorted list. Okay. So in this 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, like this. This is the concept behind the merge sort. So merge sort algorithm is also performs the steps independent of the order of input. So it also performs the same steps. Doesn't matter what type of order we are giving. If we are giving already sorted,
Sir, in A the third item is 4. In B first item is also 4.
Okay, so you are saying if both elements are same, so like 2, 3, 4, 8, and you are saying here 4, 9,
10.
10,
Yes, sir.
12. Okay, so this is the A and this is B. So A and B means from the same list. So A is the left part and B is the right part of the list. Okay. So if we have the we have 2 first, then 3 first. When we have to compare with 4 and 4, we always take this as a first step into the final list, because this is coming in the left list. This is coming in the right list. So we always pick, if elements are same, we always pick from the A.
Okay.
In this way, we maintain the stability in merge sort. Merge sort is a stable algorithm. So that means this 4 is coming in the left part of the list, and this 4 is coming in the right part of the list. So to getting the final merge list, this will come first. Okay. So order is not changed actually. So in this way, a merge sort maintains the stability, and that is stable algorithm. So yeah, so regarding this complexity part, so this algorithm always takes order of n log n time, because that is not dependent on the order of input. Okay, so this recurrence relation for this function is always remain 2t n by 2 plus n. Okay, doesn't matter what type of order. If you are giving already sorted order, still this will perform the same task. It will divide the problem okay completely and then will merge. So all will take the same time. So order of n log n. So complexity will remain always same. Okay. So yeah, this is merge function. So you can so after getting the concept, we always mention that try to implement by your own. So we have also released this time implementation algorithms. So if you are getting trouble in to understand the implementation, so you can see this additional videos which we have released this time, algorithm implementation, and see step-by-step implementation for algorithm. Okay. And now first understand the concept. Apply the concept on some input through the dry run paper and pen, and then just try to implement algorithm. Okay. So you can see all merge sort is also there. So this is the content for week 2. So all things are I think covered. So yeah, so we have mentioned this additional things regarding the data structure of Pythons. So some additional operation, how that complexity internally takes. Okay. So this copy operation, how this happen, and that how much time it takes actually. So just also go through this, so you will get the idea that suppose if we are writing some code we generally check this if any element d in L. Okay, so we write these steps to check this d exists in the L in Python. Okay, if d in L return true. So instead of linear search, we write just only this step. So this is not a constant operation. This is
order
not a
of
constant. Internally, these steps actually perform the same linear search comparisons. Then only return true. So in Python, some steps are there. Yeah, so same append. So L dot append. This operation, what it actually does. So it actually insert new element at the last. Okay, we have like 1, 3, 5, 4, 6, and we are appending 10. So what is actually happening? This new element will insert at the last. So this operation is fine. It is a constant operation internally, because we are not updating index for the remaining. We are not touching any previous elements. But what happened if we write like this: L dot insert and index, I think 0 and some, I'm not sure what is the actual method. So 10 like this. So 0 index and 10 elements. Suppose if you want to insert a new element at the first index. So that what operation internally perform actually. So indexing will update for each element. Initially, indexing is 1, 3, 5, 4, 6, 0, 1, 2, 3, 4. This one, okay. Once you are inserting a new element at the 0 index, so that means this all should be shifted to the 1 position right.
Yes.
Okay, so new element will come at the 0 index, but all will be updated. So now one element will become a 1 index, 3 will become 2, 5 will become 3, like this. Okay. So now updation is happening with all remaining element by this operation. So this operation is not a order of 1 operation. This is order of n operation. Okay. So just remember this, what type of operation is happening in the back end. Do not just consider this is a constant operation, but just by looking at a single steps in the Python.
Okay, sir. Sir, where we get that PDF?
That is the same PDF which is already released at the GitHub notes. No? So this is just a different version like this. So you can see notes are there, na? So on our PDC GitHub notes, this one.
Yes.
So you can see all are there. So same thing is there actually. Here some additional visualization is added. So the same thing is there as a PDF. Okay. So I think this link is already there in the course content in supplementary. So you can see GitHub notes. Okay. Okay. So this is the content for week 2. Just solve all the activity questions. You will get a more deeper idea of the algorithms. Solving them. Any query, anyone?
No, sir.
Okay. Okay, so if there is no query, then we can close the session. Thank you very much.
Thanks, sir. Thank you,
Thank
sir.
you so much, sir.
Thank you very much, sir.
Bye. Good night, everyone. Bye.
Thank you, sir.
Thank you, sir.